Hello, friend. Some nights the sky holds more than stars. It holds visitors, travelers from beyond slipping through the dark, silent, and quick carrying with them the dust of worlds we'll never see. And sometimes, just sometimes, they change. They glow. They turn green. Tonight we're drifting towards something rare, something that came from another star system, passed through ours only once. And as it did, it began to shine in a color no one expected. Scientists are still watching, still wondering, still asking why. Before we begin, if you find comfort in these quiet journeys through the cosmos, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell not for noise, but so the next quiet night can find you again. Now, let's drift. On a summer night in early July 2025, telescopes around the world locked onto something moving, fast, impossibly fast, over 210,000 kilometers per hour. That's roughly 130,000 miles per hour, fast enough to cross the width of the United States in under 2 minutes. But speed wasn't what made astronomers pause. It was the trajectory. The path this object was taking didn't curve like the orbits of planets or asteroids born in our solar system. It was hyperbolic, a one-way ticket. It came from somewhere else and it would never return. They named it 3I Atlas. The 3I stands for Third Interstellar. The third object we have ever confirmed came from beyond the Sun's family. The first was Oumuamua in 2017. A strange cigar-shaped visitor that tumbled through without a tail, without a glow, silent and cold. The second was 2I Borisov in 2019, a comet that behaved exactly as comets should, predictable, familiar, almost comforting in its normalcy. And now, 3I Atlas, different from both, a stranger with its own rules. When it first appeared, 3I Atlas glowed faintly red. A dusty, rusty hue, the kind you'd expect from ancient rock scattered with iron and silicates materials baked under distant suns. Scientists observed it carefully, cataloging its light, measuring its speed, tracing its origin backward through space and time. Some estimates suggest it was ejected from another star system millions of years ago, drifting alone in the cold between stars, until gravity from our sun bent its path just enough to pull it through our neighborhood. For weeks it remained red, steady, predictable. Astronomers published preliminary data. Spectroscopes analyzed its light signature. Models were built, papers were drafted. Everything pointed to a typical, if exotic, interstellar comet. Dusty, rocky, nothing too unusual. And then it changed. On September 7, 2025, two astrophotographers, Michael Yeager and Gerald Rehman, were working in Namibia. It was a special night, a total lunar eclipse. The moon's light, normally so overwhelming, was swallowed by Earth's shadow, leaving the sky darker than usual, a rare gift for those who hunt faint objects. They pointed their instruments at 3I Atlas, expecting to capture another red glow, another data point to add to the growing file. But when they processed the images, something was different. The comet wasn't red anymore. It was green, a bright, unmistakable emerald hue glowing softly around its nucleus like a lantern lit from within. The images spread quickly. Astronomers around the world requested telescope time. Observatories in Chile, Hawaii, and space-based instruments like the Hubble Space Telescope and the James Webb Space Telescope turned their eyes toward this tiny, distant visitor. Everyone wanted to know the same thing. Why? Why did it change? What happened out there so far from Earth that caused this shift from red to green? Color in astronomy is never just color. It's chemistry, it's temperature, it's history written in light. When a comet appears red, it usually means the light we're seeing is scattered by dust. Small particles of rock iron silicates the stuff of planets ground down to powder. When a comet glows green, it's almost always because of a specific molecule, diatomic carbon, written as C2. Two carbon atoms bonded together, fragile and reactive, existing only in the vacuum of space or the briefest moments of laboratory creation. When ultraviolet light from the sun hits C2, it absorbs the energy and re-emits it as green light, the same wavelength that fireflies use, the same glow you see in certain bioluminescent algae. But here's the puzzle. Spectroscopic studies of 3I Atlas taken before it turned green showed very little C2. In fact, it was described as among the most carbon chain depleted comets known. It shouldn't have had enough diatomic carbon to produce that intense green glow. So, where did it come from? Some scientists suggest it might not be C2 at all. Avi Loeb, a physicist at Harvard known for exploring unconventional ideas, proposed another possibility: cyanide, specifically a molecule called CN, which also emits light in the green-blue spectrum when energized by sunlight. And interestingly, observations from the Very Large Telescope in Chile on August 25, 2025, detected a sharp increase in cyanide production around 3I Atlas as it approached the sun. Cyanide, a word that carries weight, deadly to most life on Earth, yet common in space. It's been found in comets before, in the icy bodies of the outer solar system, even in the atmospheres of certain moons. It's a byproduct of carbon and nitrogen chemistry, the kind that happens when ices formed in the cold of interstellar space are suddenly heated. But the amount detected around 3I Atlas was unusual, not just unusual, exponential. For every step closer the comet moved toward the sun, the production of cyanide increased by nearly a factor of 10. That's not a gradual rise. That's a cascade, a chain reaction of some kind, as if the comet was waking up layer by layer, releasing gases that had been frozen for eons. And it wasn't just cyanide. Observations also detected nickel, metallic nickel vaporized and glowing in the comet's halo. Nickel is rare in comets. It's a heavy element forged in the cores of stars and scattered when those stars die. Finding it in significant amounts around 3I Atlas was unexpected, but even stranger was what wasn't there: iron. Nickel and iron almost always appear together. They're twins born in the same stellar furnaces, locked in the same meteorites, the same asteroids. Yet here nickel glowed bright while iron remained silent. It's like finding smoke without fire, a recipe missing its key ingredient. Scientists are still trying to explain it. Have you ever wondered what it would be like to hold a piece of another star system in your hand? To touch something that formed not around our sun, but around a star whose light we might not even be able to see from Earth? 3I's Atlas carries with it the chemistry of its birthplace. Every molecule, every atom, is a message written in a language we're only beginning to learn. And as it changes, as it glows green, it's telling us something. Maybe about the conditions in its home system. Maybe about the kinds of ices and rocks that form in the cold between stars. Or maybe something we haven't thought of yet. The comet continued its journey. By late September, it had brightened significantly. Telescopes tracked it day by day, watching the green glow intensify. By mid-October, it reached perihelion, the closest point to the sun, in its trajectory about 120 million kilometers away, roughly the same distance as Venus orbits. At that moment, the sun's heat would have been at its strongest, melting ices deep within the comet's core, releasing gases that had been locked away for millions, perhaps billions of years. And then, something unusual happened. Instead of a typical comet tail streaming away from the sun, images from the Hubble Space Telescope showed an extension of light pointing toward the sun, an anti-tail, a reversal of the expected pattern. Scientists suggest it might be dust particles pushed forward by pressure from vaporizing gases. But the exact mechanics are still unclear. After perihelion, 3I Atlas disappeared, not literally, but observationally. From Earth's perspective, it passed behind the sun, hidden in the glare, unreachable by most telescopes. For weeks, astronomers waited. Models predicted where it would reappear, when it would emerge from the sun's blinding light and become visible again. And on November 26, 2025, exactly 4 weeks after perihelion, the Gemini North Telescope in Hawaii captured it. still green, perhaps even greener than before. The image processed through blue, green, orange, and red filters showed a glowing halo, a teardrop shape with a faint tail, and that same anti-tail pointing sunward. The green was unmistakable. Whatever process had started in September was still happening. The comet was still active, still releasing gases, still glowing. Scientists combined data from multiple sources. The James Webb Space Telescope analyzed the chemical composition of the gas cloud surrounding 3I Atlas and found something remarkable. 87% of it was carbon dioxide CO2. Another 9% was carbon monoxide CO. Only about 4% was water H2O. For comparison, most comets in our solar system are primarily water ice. They're dirty snowballs frozen reservoirs of H2O with traces of other compounds. But 3I Atlas is different. It's dominated by carbon-based molecules. This hints at its origin. Perhaps it formed in a system where carbon was more abundant than oxygen. Or perhaps it formed farther from its parent star, in a region where carbon dioxide could freeze solid while water remained gaseous and escaped. We don't know yet. But every measurement adds a piece to the puzzle. There's something humbling about watching an object like this. It traveled for millions of years, through absolute darkness, through the void between stars, where temperatures hover just a few degrees above absolute zero. It carried with it the dust and ice of its birthplace, a world we'll never visit, a star we might never identify. And then, by chance, or perhaps inevitability, it fell toward our sun, and for a few months, we got to see it, to measure it, to wonder about it. And it changed before our eyes, from red to green, from dust to gas, from silent to glowing. By mid-December 2025, 3I Atlas made its closest approach to Earth. Not dangerously close, about 280 million kilometers away, roughly twice the distance from Earth to the Sun, but close enough for detailed observations. Space agencies, including NASA and ESA, pointed their most sensitive instruments at it. The Europa Clipper spacecraft, designed to study Jupiter's moon, took a detour to capture images. X-ray observatories like XMM Newton and X-RISM detected faint X-ray emissions, the result of solar wind particles colliding with the comet's gas cloud, ionizing atoms and causing them to glow in wavelengths invisible to the human eye but bright to specialized detectors. Even ground-based observatories joined in from Chile to Hawaii to Namibia. Every continent with a clear sky turned at least one telescope toward this green visitor. And now, as we speak, 3I Atlas is leaving, moving away from the sun, away from Earth, accelerating back into the cold. In a few years, it will pass beyond the orbit of Neptune. In a few decades, beyond the Kuiper Belt. And eventually, it will return to the space between stars, carrying with it whatever remains of its ices and gases, glowing faintly until the sun's light is too weak to energize its molecules, and it goes dark again, silent, alone, a traveler continuing a journey that may never end. But we saw it, we measured it, we watched it glow green. And in doing so, we learned something about the universe, about chemistry, about the diversity of objects that drift through the dark, about how much we still don't know. What makes a comet change color? What chemistry hidden in the ice waits for the right moment, the right temperature to reveal itself? And what does that tell us about the places these objects come from? These are the questions we carry with us as we move deeper into this story. Because 3I Atlas didn't just change color randomly, there's a reason, a process, a sequence of events written in molecules and light. And as we continue, we'll explore what science has discovered, what it suspects, and what it still doesn't understand. We'll drift through the chemistry of color, the history of interstellar visitors, and the strange, beautiful anomalies that make 3I Atlas unlike anything we've seen before. The green glow is just the beginning. 3 times in human history, we've watched something arrive from beyond. 3 times the universe sent us visitors, and each time they were nothing like each other. The first was a mystery wrapped in silence. The second, familiar and almost ordinary. And the third began as a red stranger, a wanderer dressed in rust and dust moving through our solar system with a speed that announced its origin before we could even measure it. But what made this visitor different wasn't just where it came from. It was what it would become. In 2017, on October 19th, a telescope in Hawaii detected something unusual: pan-stars. One, a survey telescope designed to scan the sky for near-Earth objects, captured a faint streak of light moving against the background of stars. At first, astronomers thought it might be an asteroid or a comet from the outer reaches of our solar system. But as they calculated its trajectory, something became clear. Its path was hyperbolic, not elliptical, not bound to the sun. It was moving too fast at an angle too steep, coming from a direction that didn't align with any known object in our solar neighborhood. It had come from interstellar space, from another star system. They named it Wanyai Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first. Oumuamua was strange in almost every way. It was elongated perhaps 10 times longer than it was wide, tumbling end over end as it moved. Some estimates suggested it was about 400 meters long and only 40 meters wide, shaped like a cigar or perhaps a needle. It reflected light in a way that suggested a rocky or metallic surface, possibly reddish in color, due to cosmic radiation damage over millions of years. But what puzzled scientists most was what it didn't do. It didn't glow. It didn't develop a tail. It showed no signs of outgassing, no release of ice or vapor that would indicate it was a comet. It was inert, silent, a cold rock tumbling through space. And yet it accelerated, not much but measurably. As it swung around the sun and began its journey back into interstellar space, instruments detected a small but consistent push, a non-gravitational acceleration that couldn't be explained by the sun's gravity alone. Scientists proposed several ideas. Perhaps it was outgassing after all, but at levels too low to detect visually. Perhaps it was radiation pressure from sunlight pushing against its surface. Or perhaps it was something else entirely. The debate continues even now, years after Oumuamua disappeared beyond the reach of our telescopes, fading into the dark from which it came. Then, in 2019, we got a second chance. On August 30th, an amateur astronomer named Gennady Borisov, working with a telescope he built himself in Crimea, spotted a fuzzy object moving through the constellation of Cancer. He reported it to the Minor Planet Center, and within days, professional observatories confirmed what he had found. Another interstellar visitor. They named it 2I Borisov, the second confirmed object from beyond our solar system. But unlike Oumuamua, Borisov behaved exactly as expected. It was a comet, a classic textbook comet. It developed a tail. It released gas and dust. Spectroscopes detected water vapor, carbon monoxide, and cyanide, the standard ingredients of comets formed in the cold outer regions of planetary systems. It even looked like comets from our own Oort cloud, that distant shell of icy bodies surrounding the sun at the edge of its gravitational influence. Scientists were relieved in a way. Borisov made sense. It fit the models. It was proof that other star systems produced objects similar to ours, that the chemistry of planet formation wasn't unique to the sun. Observations from the Hubble Space Telescope, the Atacama Large Millimeter Array in Chile, and dozens of other instruments tracked Borisov for months as it swung through the inner solar system and departed. It was studied more thoroughly than Oumuamua ever was, because this time we knew what to expect. We had time to prepare, and when it faded back into interstellar space, it did so quietly, predictably leaving behind a wealth of data and very few mysteries. Two visitors. Two completely different experiences. Oumuamua, strange and silent, defying explanation. Borisov, familiar and comforting, a reminder that the universe follows patterns we can understand. And then, 6 years after Oumuamua and 6 years after Borisov, a third object appeared. In late June 2025, the Atlas Survey Telescope's Asteroid Terrestrial Impact Last Alert System detected a faint point of light moving rapidly across the sky. Initial observations suggested it might be another asteroid, another near-Earth object to catalog and monitor. But within 48 hours, trajectory calculations revealed the truth. Hyperbolic orbit, interstellar origin, another visitor. They designated it 3I Atlas, the third interstellar object confirmed by humanity. At first, 3I Atlas seemed unremarkable. It was faint, distant, and difficult to observe. Early spectroscopic data showed a reddish hue consistent with a surface covered in dust, and organic compounds, materials darkened by eons of exposure to cosmic rays. This was expected. Most objects in space, especially those traveling through the void between stars, accumulate a layer of radiation-damaged material that appears red or brown. It's the same process that gives Mars its rusty color, the same reason some asteroids and moons look reddish. Organic molecules, long chains of carbon and hydrogen, break down under radiation, leaving behind a residue called Tholen's complex organic compounds that absorb blue light and reflect red. Astronomers cataloged 3I Atlas and began planning observing campaigns. Telescopes around the world requested time. Space agencies coordinated. Everyone wanted a piece of this visitor, a chance to study it before it left. But in those early days, it seemed ordinary, just another interstellar traveler, interesting, but not extraordinary. It wasn't glowing. It wasn't brightening unexpectedly. It was just moving fast and silent on a path that would take it through the inner solar system and out again, never to return. But then something changed. In early September, as 3I Atlas moved closer to the Sun, observers began noticing unusual activity. The object brightened, not dramatically, but enough to attract attention. Photometric measurements showed an increase in reflected light, suggesting either that more surface area was being exposed, or that material was being ejected, creating a haze around the nucleus. And then came the color shift. Images taken on September 7th, during a total lunar eclipse when the sky was exceptionally dark, showed a faint greenish tinge around the comet. Not strong, but present. A glow that hadn't been there before. This was unexpected. Comets can appear green, but usually only when they're actively releasing large amounts of gas, particularly diatomic carbon. And earlier studies of 3I Atlas suggested it was depleted in carbon chains, lacking the molecules needed to produce that green emission. So, why was it glowing? Was the initial data wrong, or had something changed as the comet warmed? Scientists scrambled to gather more observations. Spectroscopes were trained on the object, analyzing the wavelengths of light it emitted and reflected. And what they found raised more questions than it answered. The green wasn't just diatomic carbon, or at least not only diatomic carbon. Observations from the Very Large Telescope in Chile detected a sharp increase in cyanide CN molecules in the gas cloud surrounding 3I Atlas. Cyanide also emits in the green-blue spectrum when energized by sunlight, and the levels detected were unusually high. Moreover, the production rate was increasing exponentially. For every astronomical unit closer the comet moved toward the Sun, 1 AU is the distance from Earth to the Sun, about 150 million kilometers. The amount of cyanide increased by a factor of roughly 10. That kind of exponential growth suggested something unusual was happening beneath the comet's surface, some kind of cascade or chain reaction, as heat penetrated deeper into the icy nucleus. But that wasn't the only anomaly. Spectroscopes also detected nickel, metallic nickel vaporized by the heat and glowing in the comet's halo. Nickel is rare in comets. It's a heavy element typically locked in solid rock or metal, not easily vaporized. Its presence suggested that 3I Atlas contained metallic grains, perhaps remnants of the star system, where it formed dust particles forged in a supernova and incorporated into the comet's icy matrix. What made it even stranger was the absence of iron. Nickel and iron are almost always found together in meteorites and asteroids because they form together in the cores of dying stars and are ejected together when those stars explode. Yet here nickel was prominent and iron was missing, or at least it wasn't being detected in the expected quantities. Have you ever tried to solve a puzzle where the pieces don't quite fit, where you think you understand the picture, but then you find an extra piece or a piece is missing, and suddenly everything you thought you knew feels uncertain? That's where scientists found themselves with 3I Atlas. Every measurement seemed to contradict something else. It was carbon depleted, but glowing green. It was producing cyanide in vast quantities. It had nickel, but no iron, and its brightness was increasing faster than models predicted. Some researchers began comparing 3I Atlas to the two previous interstellar visitors. Oumuamua had been a mystery because it did almost nothing. It was inert cold, showing no signs of the activity typically associated with comets. It just tumbled through space, silent and enigmatic. Borisov, on the other hand, had been a relief because it did everything expected. It behaved like a comet from our own solar system, releasing gas and dust in predictable patterns. But 3I Atlas. It was doing things, but not the right things. Or rather, it was doing the right things in the wrong proportions at the wrong times with the wrong chemistry. Scientists began to wonder if 3I Atlas represented a new category, not a rocky asteroid like Oumuamua seemed to be. Not a standard icy comet like Borisov, but something in between or something entirely different. Perhaps it formed in a system unlike ours where the balance of elements was different. Perhaps it formed farther from its parent star in a region so cold that even carbon dioxide and carbon monoxide froze solid, creating a comet dominated by carbon-based ices rather than water. Or perhaps it was older than the other two, having spent more time in interstellar space, accumulating layers of processed material that change its chemistry in ways we don't yet understand. One of the challenges in studying interstellar objects is that we get so little time with them. Oumuamua was discovered only after it had already passed its closest point to the sun and was heading back out. By the time astronomers realized what it was already leaving. Borisov was discovered earlier in its trajectory, giving scientists a few months to study it before it departed. But even then, the window was short. These objects move fast. They're not bound to the sun, not captured by its gravity. They're just passing through, and once they're gone forever. No second chances, no follow-up observations years later. Every measurement has to be taken in the moment, or it's lost. With 3I Atlas astronomers were determined to learn as much as possible. Observing campaigns were coordinated across continents. Ground-based telescopes in Chile, Hawaii, South Africa, and Australia tracked it nightly. Space-based observatories like Hubble and Webb scheduled time. Even X-ray satellites designed to study distant galaxies and black holes turned their instruments toward this small, faint comet, hoping to detect high-energy emissions from the interaction of solar wind with its gas cloud. Data poured in, spectra were analyzed, models were updated, and with each new observation, the picture became both clearer and more complex. By mid-September, it was clear that 3I Atlas was unlike either of its predecessors. It wasn't silent like Oumuamua. It wasn't predictable like Borisov. It was active, changing, revealing new layers with each passing week. And the red color, that initial rusty hue, was fading, replaced by the green glow that would come to define it in the public imagination. But why? What triggered the shift? Was it simply heat from the sun, melting deeper layers of ice, exposing fresh material that had been shielded for millions of years? Or was something else at play? Some chemical process unique to this particular comet, this particular visitor. Scientists noted that 3I Atlas had likely been traveling through interstellar space for an immense amount of time. based on its trajectory and speed estimates, suggest it was ejected from its home system millions, possibly tens of millions of years ago. That's an almost incomprehensible duration. During that time, it would have been exposed to cosmic rays' high-energy particles from distant supernovae and the galactic center radiation that slowly alters the chemical structure of any material it touches. Organic molecules break apart and reform into new compounds. Ices crystallize and become amorphous. Metals oxidize even in the near vacuum of space. The surface of an interstellar object is a laboratory for slow, steady chemistry processes that take eons to complete. And when that object finally encounters a star again, when it falls into the warmth of a new sun, all that accumulated damage, all those altered molecules begin to react. Heat penetrates the surface. Ices sublimate, turning directly from solid to gas without passing through a liquid phase. Gases expand, cracking the surface, releasing material that's been locked away. It's a kind of awakening. A frozen archive suddenly opened, and what emerges depends on what was there to begin with and what happened to it during the long, cold journey between stars. Perhaps that's what we were seeing with 3I Atlas, not just a comet warming up, but a library of chemistry page by page revealing itself as the sun's heat turned the pages. First the surface dust red and ancient, then deeper ices, carbon dioxide and carbon monoxide materials that require more heat to vaporize. And finally, even deeper, the cyanide and nickel traces of the star system where it was born, elements forged in stellar furnaces and scattered into space only to be gathered up by a young comet billions of years ago and carried across the galaxy. In those early weeks as 3I Atlas moved from red to green, astronomers were witnessing a transformation, a visitor from another star waking up, responding to the warmth of our sun, releasing the secrets it had carried for so long. And as it did, it became clear that this wasn't going to be a simple story. This wasn't going to be another Oumuamua, silent and inscrutable. This wasn't going to be another Borisov, comfortable and familiar. This was something new, something that would challenge assumptions, raise questions, and remind us that the universe is far more diverse, far more strange than we often imagine. The red stranger had arrived, but it wouldn't stay red for long. And as the green glow began to spread, wrapping around the nucleus like a soft, glowing halo, scientists knew they were watching something rare. A transformation not just of color, but of understanding. Because to understand why a comet changes from red to green, you have to understand the chemistry of comets themselves, the molecules, the reactions, the delicate balance of heat and cold light and shadow. And that's where we turn next, into the chemistry that makes a comet glow, the science that explains why some visitors shine emerald in the dark, and why 3I Atlas, against all expectations, join their ranks. Color is memory. Every hue carries a story, written in atoms and light. When you see green in the night sky glowing softly around a distant comet, you're not just seeing beauty, you're seeing chemistry, ancient chemistry, the language of molecules speaking across the void. But why green? Why not blue or yellow or red? What makes some comets shine emerald while others remain pale and dusty? The answer lies not in magic, but in the delicate dance between sunlight and molecules, so fragile they can barely exist. And once you understand that dance, the universe begins to glow differently. Everything does. To understand why comets change color, we need to start with what a comet actually is. Most people imagine them as solid objects, rocks with tails, fireballs streaking through space. But that's not quite right. A comet is more like an onion. Layers upon layers. At the center is the nucleus, a solid core of ice and rock, typically a few kilometers across, sometimes smaller, occasionally much larger. This nucleus is ancient, often as old as the solar system itself, formed 4.6 billion years ago in the cold outer regions where planets were being born. It's made primarily of water ice, but mixed in are other ices, frozen gases that only become solid at temperatures far below anything we experience on Earth. Carbon dioxide, carbon monoxide, methane, ammonia. And mixed with these ices are dust particles, tiny grains of rock and metal silicates, and organics, the leftover debris from the cloud of gas and dust that collapse to form a star and its planets. For most of a comet's life, this nucleus remains frozen dormant, unchanged. If the comet stays in the outer solar system, far from the sun, it can remain like this for billions of years, a cold, inert lump of ice and rock drifting in darkness. But when a comet's orbit brings it closer to the sun, when the temperature begins to rise, something beautiful happens. The ice starts to sublimate, not melt sublimate. It turns directly from solid to gas, skipping the liquid phase entirely, because the pressure in space is so low that liquid can't exist. And as the ice sublimates, it releases gas streams of molecules that expand outward from the nucleus, forming what we call the coma, a hazy atmosphere that can grow to be larger than Earth itself, sometimes even larger than Jupiter. This coma is where color lives. It's not the nucleus we see glowing. The nucleus is too small, too dark. What we see is the coma, the cloud of gas and dust surrounding the nucleus. And the color of that coma depends entirely on which molecules are present and how they interact with sunlight. Light from the sun isn't just illumination, it's energy. Each photon carries a specific amount of energy determined by its wavelength. Ultraviolet light carries more energy than visible light, which carries more energy than infrared. When these photons strike molecules in the coma, they can be absorbed. The molecule takes in the energy, and one of its electrons jumps to a higher energy state. But electrons don't like to stay in higher energy states. They want to return to their ground state, their resting position. And when they do, they release that energy as light. Not always the same wavelength they absorbed, but a specific wavelength determined by the structure of the molecule. This process is called fluorescence. It's the same principle behind glow-in-the-dark toys, the same reason certain minerals glow under ultraviolet light, the same mechanism that makes fireflies shine. A molecule absorbs high-energy light, holds that energy for a brief moment, and then releases it as a different color. And in comets, the most famous fluorescent molecule is diatomic carbon C2, two carbon atoms bonded together. It's an unusual molecule. On Earth, carbon prefers to bond with oxygen, forming carbon dioxide or carbon monoxide, or it bonds with hydrogen, forming methane and other hydrocarbons, or it bonds with itself in long chains and rings, forming everything from diamonds to the organic molecules in living cells. But two carbon atoms bonded together and nothing else. That's rare. It's unstable. It only exists in high-temperature environments like flames or in the near vacuum of space where there's nothing for it to react with. When ultraviolet light from the sun strikes C2 molecules in a comet's coma, those molecules absorb the energy and re-emit it at a wavelength of about 518 nanometers. That's green. A bright, pure green, the same shade you see in certain fireflies, the same glow emitted by some bioluminescent algae. And because this emission is so strong, even a relatively small amount of C2 can make an entire comet appear green. It's striking, unmistakable, a color that stands out against the blackness of space. But here's something interesting. The green glow is almost always confined to the coma. It doesn't extend into the tail. If you look at images of green comets, you'll notice the head glows green, but the tail remains white or yellowish. Why? Because C2 molecules are fragile. Sunlight not only excites them, it also destroys them. The same ultraviolet photons that cause fluorescence can also break the bond between the two carbon atoms, splitting C2 into individual carbon atoms, which don't emit green light. This process, called photodissociation, happens quickly. Within about 50,000 kilometers of the nucleus, most C2 molecules have been destroyed. That's roughly the distance from Earth to its nearest satellite orbit, a tiny fraction of the millions of kilometers a comet's tail can stretch. So, the green glow marks a boundary, a region close to the nucleus, where molecules are still intact, still fluorescing before they're torn apart by the sun's radiation. Scientists have studied this phenomenon for over a century. In the 1860s, astronomers using early spectroscopes noticed bright green emission lines in the spectra of comets. They didn't know what molecule was responsible at the time. Some thought it might be a new element, something unique to comets. They even gave it a name nebulium, after the nebulous clouds where it appeared. But later in the early 1900s, laboratory experiments identified the true culprit. Not a new element, but a simple molecule. C2, diatomic carbon. And once they knew what to look for, they found it in many comets, especially those rich in carbon-based ices. But not all comets glow green. Some remain white or yellowish throughout their journey. The difference comes down to composition. Comets formed in different regions of the solar system or in different star systems can have very different chemical makeups. A comet that formed closer to the sun might be richer in rocky materials and poorer in volatile ices. A comet that formed farther out in the coldest regions might be dominated by water ice with only traces of carbon compounds. And the amount of C2 produced depends on the original chemistry of the comet and how that chemistry evolves as it warms. Interestingly, C2 isn't usually present in the ice itself. What's frozen in the nucleus is more complex carbon compounds, long chains of hydrocarbons, organic molecules, built from carbon, hydrogen, oxygen, and other elements. When these molecules sublimate and are exposed to sunlight, they break apart. Ultraviolet radiation is harsh. It tears molecules into fragments. And one of the fragments produced is C2. So, the green glow is actually a byproduct of destruction. The comet's original organic molecules are being ripped apart by the sun, and C2 is one of the pieces left behind, glowing briefly before it too is destroyed. There's another molecule that can produce a greenish glow, though in a slightly different shade. Cyanide, or more precisely the CN radical, a molecule made of one carbon atom and one nitrogen atom. CN also fluoresces when struck by ultraviolet light, emitting in the blue-green part of the spectrum around 388 nanometers. This is a slightly different color than C2, more blue-green than pure green, but to the eye, especially when looking at a faint comet, the difference can be hard to distinguish. CN is more common in comets than C2 in some ways, because nitrogen is a relatively abundant element. And many comets contain nitrogen-bearing molecules like ammonia or hydrogen cyanide frozen in their ices. Hydrogen cyanide HCN is particularly interesting. It's a simple molecule, just hydrogen, carbon, and nitrogen, but it's also highly reactive and toxic. On Earth, it's used in industrial processes and infamously as a poison. But in space, it's just another molecule, one of many, that form in the cold clouds where stars and planets are born. When a comet warms and HCN sublimates, it can be broken apart by sunlight, producing CN radicals. And those radicals glow. So a comet rich in HCN will produce a strong CN emission, adding to or even dominating the green-blue glow. Now, here's where things get complicated. Different comets have different ratios of C2 to CN. Some are C2 rich, glowing a purer green. Others are CN rich with more of a blue-green tint. And some have very little of either, remaining relatively colorless. Scientists use these ratios as a kind of chemical fingerprint, a way to classify comets and understand their origins. In the 1980s, a study by astronomer Michael Ahern and his colleagues analyzed the spectra of dozens of comets and found they could be divided into two broad categories based on their carbon chemistry. Some were typical, with high levels of both C2 and CN relative to water. Others were depleted, with much lower levels. This suggested that not all comets formed under the same conditions, that the chemistry of the early solar system varied from place to place, and the comets preserve a record of those variations. But predicting which comets will glow green isn't always straightforward. In 2013, Comet Ison was expected to put on a spectacular show as it passed close to the Sun. Astronomers predicted it would become one of the brightest comets in decades possibly visible in daylight, and early observations showed a beautiful green coma, rich in C2 and CN. But as it approached the Sun, something went wrong. The comet began to fragment. The nucleus broke apart, unable to withstand the Sun's heat and tidal forces. By the time it reached perihelion, it had essentially disintegrated, leaving behind only a faint smudge of dust. The green glow faded, and the comet that was supposed to be spectacular became a disappointment. It was a reminder that comets are fragile, and that even with all our instruments and models, we can't always predict what will happen. Then there's Comet Lovejoy, discovered by Australian amateur astronomer Terry Lovejoy in 2011. It was a sun grazer, a comet, whose orbit took it incredibly close to the Sun, passing within 140,000 kilometers of the solar surface, closer than the Moon is to Earth. No one expected it to survive. The heat and radiation should have vaporized it completely. But somehow, a fragment of the nucleus survived, and as it emerged from behind the Sun, it glowed brilliantly green. Images from observatories around the world showed a bright emerald head with a long, pale tail stretching millions of kilometers. The green was so intense because the comet was releasing enormous amounts of gas, C2 and CN, flooding the coma, as the superheated nucleus sublimated at an extreme rate. It was a spectacular display, a comet that defied the odds and gave us one of the most beautiful green glows ever recorded. Another famous green comet is Comet Hartley 2, visited by NASA's Deep Impact spacecraft in 2010. As the spacecraft flew past, it captured detailed images of the nucleus, revealing an elongated peanut-shaped body actively jetting gas and dust into space. Spectroscopic instruments on the spacecraft measured the composition of the coma and found high levels of C2, explaining the comet's strong green color. But they also found something unexpected. The two lobes of the nucleus were releasing different materials. One end was jetting water vapor and dust, while the other was releasing carbon dioxide. It was as if the comet had two personalities, two different chemical environments frozen side by side. This discovery suggested that comets might not be uniform, inside that they could have layers or regions with distinct compositions, each contributing differently to the overall coma. Scientists have also noticed that the green glow can vary over time, even for the same comet. As a comet approaches the Sun, it might start with little or no green emission, then develop a strong green coma, and then fade again as it moves away. This happens because the production of C2 and CN depends on temperature. Close to the Sun, the heat penetrates deeper into the nucleus, reaching layers that were previously frozen. New ices sublimate, new molecules are released, and new chemistry begins. Farther from the Sun, only the surface ices sublimate, and the chemistry is simpler, dominated by water vapor and whatever was on the outermost layer. There's also a phenomenon called the Swan bands, named after the scientist who first studied them in detail. These are specific wavelengths of light emitted by C2, creating a pattern of bright and dark lines in the spectrum. By analyzing the Swan bands, astronomers can determine not just that C2 is present, but how much is present, how fast it's moving, and even the temperature of the gas. It's like reading a detailed report written in light, a message from the comet telling us about its chemistry and its history. But what about comets that don't glow green? What determines whether a comet will produce C2 and CN or remain colorless? The answer lies in the original composition of the ices and the conditions under which the comet formed. Comets that formed in colder regions farther from the Sun tend to be richer in volatile ices like carbon monoxide and carbon dioxide. These ices sublimate easily even at relatively low temperatures, and when they break apart under sunlight, they produce carbon radicals that can combine to form C2. Comets that formed closer in warmer regions might be richer in water ice and rockier materials with fewer carbon-rich compounds. These comets tend to glow white or yellowish, reflecting sunlight off dust particles rather than fluorescing from gas. There's also the age of the comet to consider. Comets that have passed close to the sun many times, like Halley's Comet, have lost much of their volatile material. Each time they warm, they release gas and dust, and over time the surface becomes coated with a layer of non-volatile residue, a crust of dust, and heavy molecules that insulates the ice beneath. This crust can reduce the amount of gas released, making the comet dimmer and less colorful. Eventually, after many orbits, a comet can become essentially inactive, more like an asteroid than a comet, no longer producing a coma or tail. So, when we look at a green comet, we're seeing something specific. We're seeing a comet rich in carbon-based ices, actively releasing gas with enough ultraviolet light from the sun to excite C2 and CN molecules, but not so much that those molecules are immediately destroyed. It's a balance, a sweet spot of distance and chemistry and time, and it's beautiful not just visually, but scientifically. Each green glow is a window into the comet's composition, its history, its journey through space. And that brings us back to 3I Atlas. When it first appeared, it was red, suggesting a dusty surface, organic-rich, carbon-depleted. But as it approached the sun, it turned green, intensely green. And the question became, why? What changed? Did the comet have hidden layers of carbon-rich ice beneath its surface? Did the chemistry evolve in unexpected ways as it warmed? Or was there something unique about this interstellar visitor? Something that made it different from comets born in our solar system? The answers would come slowly, observation by observation, spectrum by spectrum. As 3I Atlas continued its journey toward the sun, growing brighter, glowing greener, revealing itself, molecule by molecule. And as it did, it would show us that the chemistry of color is not just a curiosity, but a key to understanding where comets come from, what they're made of, and what they can teach us about the universe beyond our own small corner of space. Sometimes change happens in an instant. One moment, the world is one way. The next, it's different. And you can point to the exact second it shifted. September 7th, 2025 was one of those moments. The night the moon went dark and a comet turned green. It was a total lunar eclipse, the moon sliding into Earth's shadow, dimming from silver to copper to near black. And in that rare darkness, with the moon's light extinguished, the sky opened. Faint objects normally drowned out became visible. Stars sharpened. Nebulae glowed. And in Namibia, 2 astrophotographers aimed their cameras at a red visitor from beyond, expecting nothing unusual. But what they captured would change everything. On that eclipse night, Michael Yeager and Gerald Raymond set up their equipment in the Namibian highlands, one of the darkest places on Earth. They had been tracking 3I Atlas for weeks, contributing to the global effort to document this third interstellar visitor. Their goal was simple: capture high-resolution images during the eclipse, when the absence of moonlight would allow longer exposures without light pollution. They calibrated their telescopes, aligned their tracking systems, and waited for totality. When the moon finally darkened completely, they began their exposures. Multiple frames stacked to reduce noise, filtered to isolate specific wavelengths. Standard procedure, routine work. Except the images that came back were anything but routine. When they processed the data, they saw it immediately. The comet had changed. Where previous observations had shown a faint reddish glow, diffuse and dusty, the new images revealed something startling. A bright green hue concentrated around the nucleus, spreading outward in a soft halo. Not subtle, not ambiguous. Green. Unmistakably green. They checked their calibration. They reviewed their filters. They compared with images from earlier in the week. Everything confirmed it. 3I Atlas had transformed. Within days, perhaps even hours, the comet had shifted from red to emerald, as if someone had turned on a light inside. The images were posted online, immediately shared with the astronomical community. and within hours, observatories around the world were scrambling to confirm. Telescopes in Chile, Australia, South Africa, and Hawaii pointed skyward. Everyone wanted to see it for themselves, and every observation came back with the same result: green. The comet was glowing green. But why? And more importantly, why now? What had happened between the last red observations in late August and this September night that triggered such a dramatic transformation? To understand the timing, we need to look at where 3I Atlas was in its journey. By early September, the comet had reached approximately 2.5 astronomical units from the Sun. 1 AU is the distance from Earth to the Sun, about 150 million kilometers. So, 3I Atlas was roughly 375 million kilometers from the Sun, somewhere between the orbits of Mars and the asteroid belt, still quite far out. At that distance, the Sun's heat is weak only about 16% of what we feel on Earth. But for a comet, especially one coming from the cold of interstellar space, it's enough. Enough to start warming the surface, enough to penetrate the outer layers, enough to trigger sublimation. Scientists believe what happened was this for months. As 3I Atlas approached the Sun, the outermost layer of its nucleus had been slowly warming. This outer layer, exposed to cosmic radiation for millions of years, had been processed, darkened, turned into a reddish-brown crust of complex organic compounds called tholins. These molecule-long chains of carbon and hydrogen, broken and reformed by radiation, don't sublimate easily. They're stable refractory, requiring high temperatures to vaporize. So, as the comet warmed, this crusty layer remained intact, releasing only small amounts of dust, giving the comet its initial red appearance. But beneath that crust, deeper layers waited. Layers of pristine ice frozen since the comet's formation, untouched by radiation, rich in volatile compounds. And as the Sun's heat slowly penetrated deeper, conducted through the crust, those ices began to respond. First, the most volatile molecules, those that sublimate at the lowest temperatures: carbon monoxide, carbon dioxide. And as these gases formed and expanded, they created pressure. Tiny fissures opened in the crust. Gases began to escape, and with them came the chemistry of the comet's interior. The timing of the color change suggests that by early September, the heat had finally reached a critical depth. A layer rich in carbon compounds, perhaps hydrocarbons or more complex organics, began to sublimate. And when these molecules were released into the sunlight, ultraviolet radiation tore them apart, fragmenting them into simpler molecules. Among those fragments, diatomic carbon C2 and cyanide radicals CN, the green molecules, the ones that glow. But there was more to the story. Spectroscopic observations from the Very Large Telescope in Chile, taken on August 25th, just days before the color change became visible, had detected something unusual: a sharp increase in cyanide production, not gradual, exponential. The amount of CN in the coma was growing at an extraordinary rate, doubling, tripling, increasing tenfold with each passing week. And this wasn't just cyanide. Other molecules were spiking too. Nickel compounds, trace metals vaporized from dust grains embedded in the ice. The comet was waking up layer by layer, revealing its interior chemistry. Scientists proposed that what we witnessed on September 7th wasn't the beginning of the transformation, but the moment it became visible. The green glow had likely been building for days, perhaps weeks, growing stronger as more and more gas was released. But it took the perfect conditions, the darkness of the eclipse, the sensitivity of the equipment, and the skill of the observers to capture it. Before that night, the green emission might have been there, but too faint to see against the background sky. The eclipse gave us the gift of darkness, and in that darkness, the green light finally stood out. There's a lesson here about observation. In science, discovery often depends as much on when you look as what you're looking at. If Jaeger and Rayman had observed a week earlier or a week later, they might have missed the exact moment of transition. If there hadn't been an eclipse providing that rare darkness, the green might have remained hidden a bit longer. Timing matters. Conditions matter, and sometimes the universe aligns in just the right way to show us something extraordinary. The green transformation also revealed something about the structure of 3I Atlas. The fact that it could shift so dramatically suggested the nucleus was layered with distinct chemical zones. Imagine cutting an onion. Each layer is slightly different formed at a different time under different conditions. Comets are similar. They don't form uniformly, as they accrete material in the early solar system, or in this case, another star system. They gather ice and dust from their surroundings. But those surroundings change. Closer to the forming star, temperatures are higher, and certain molecules dominate. Farther out in the cold outer regions, different ices freeze. And if conditions change over time, if the young star brightens or dims, if nearby supernovae inject new material, the chemistry changes. Each layer records a moment in the comet's formation, a snapshot of the conditions at that time. When 3I Atlas began its journey through our solar system, the first material to sublimate was the outermost layer, the most processed, the most altered by radiation. This gave us the red phase. But as heat penetrated deeper, it reached layers that had been shielded, preserved, protected. And those layers had different chemistry. They were richer in volatiles, richer in carbon compounds, richer in the molecules that produce green light. So the color change wasn't random, it was sequential, a story told in chapters, each layer revealing itself as the sun's warmth turned the pages. Interestingly, not all comets follow this pattern. Some remain consistently colored throughout their journey. Others show fluctuations, brightening and dimming, changing hue unpredictably. Comet 67P Churyumov-Gerasimenko, visited by the European Space Agency's Rosetta mission in 2014, was intensely studied for over 2 years. Instruments on the Rosetta spacecraft and its lander, Philae, measured the comet's composition in unprecedented detail. They found that the nucleus was incredibly heterogeneous, with some regions dominated by water ice, others by carbon dioxide, and still others by complex organics. Jets of gas erupted from specific locations not evenly across the surface, suggesting that the interior structure was complex with pockets and layers and boundaries between different materials. And as the comet warmed, different regions activated at different times, each contributing its own chemistry to the coma. 3I Atlas appeared to be following a similar pattern, but with a twist. It wasn't just heterogeneous, it was sequentially heterogeneous, revealing its layers in order as heat penetrated inward. And the green layer, the one rich in carbon compounds, was buried beneath the red crust, waiting for the right moment to emerge. Scientists began to wonder, were there more layers beneath? Would the comet change color again as it got even closer to the sun? What other chemistry was hidden inside, waiting to be revealed? The exponential increase in cyanide production added another puzzle. Exponential growth is unusual in nature. It suggests a feedback loop, a process that accelerates itself. In the case of 3I Atlas, one possibility is that as gas escaped from the interior, it created channels through the crust pathways for more gas to follow. And as more gas escaped, the channels widened, allowing even more gas to flow. It's similar to what happens in a geyser. Pressure builds beneath the surface. A small crack opens. Water and steam rush out. The flow erodes the crack, making it larger. More water escapes. The pressure drops briefly, then builds again, and the cycle repeats. In 3I Atlas, the geyser might have been chemical rather than thermal, driven by sublimation rather than boiling, but the principle is the same. A small release triggers a larger release, which triggers an even larger one, growing exponentially until a new equilibrium is reached. The presence of nickel detected alongside the cyanide added yet another layer of mystery. Nickel is a heavy element not easily vaporized. It requires temperatures above 400 degrees Celsius to boil. Yet, here it was present in significant amounts in the gas cloud around 3I Atlas, far from the sun, where temperatures were well below zero. How could nickel be vaporizing in such cold conditions? The answer lies not in the bulk temperature, but in localized heating. When sunlight strikes dust, particles embedded in the ice, those particles can absorb the light and convert it to heat. If a dust particle contains metallic nickel, and if it's small enough, just a few nanometers across, it can heat up significantly hot enough to vaporize. The nickel atoms then escape into the gas cloud, where they can be detected spectroscopically. But this raises a question: why nickel and not iron? The two metals almost always occur together because they form together in the cores of dying stars and are ejected together in supernova explosions. Yet observations of 3I Atlas showed strong nickel emission, but little to no iron. Some scientists suggest the iron might be locked in larger grains too large to heat sufficiently. Others propose that the iron might be oxidized, bound to oxygen or sulfur, forming compounds that don't vaporize as easily. Or perhaps the original composition of 3I Atlas, formed in a different star system under different conditions, simply had more nickel than iron. It's unusual, but not impossible. Each star system is unique with its own balance of elements determined by the star's mass age and the history of supernova events in its neighborhood. As the green glow intensified through September, astronomers continued to gather data. Spectroscopes measured the exact wavelengths of light emitted by the coma, identifying not just C2 and Cn, but also traces of other molecules. Hydroxyl, OH, a fragment of water molecules broken apart by sunlight. Carbon monoxide, CO, released directly from sublimating ice. And hints of ammonia, NH3, detected faintly in infrared observations. Each molecule added a piece to the puzzle, a clue about what 3I Atlas was made of and where it came from. Photometric measurements tracked the brightness of the comet, and these revealed another interesting pattern. The green glow wasn't constant. It fluctuated, brightening and dimming over periods of hours to days. This suggested the nucleus was rotating, and different regions of the surface were being illuminated as it turned. If the nucleus had active regions, areas where gas was being released more vigorously, those regions would glow more brightly when they faced the sun and dim when they rotated into shadow. By analyzing these fluctuations, scientists estimated the rotation period of 3I Atlas to be somewhere around 12 to 18 hours, though the exact value remained uncertain due to the comet's distance and faintness. There's something almost poetic about watching a comet transform. It's a reminder that nothing in the universe is truly static. Everything evolves, changes, responds to its environment. A comet that appears one way today might look completely different in a week, a month, a year. And each change tells a story, a record of the physics and chemistry at work, the interplay of heat and cold light and shadow, solid and gas. In a way, comets are like living things, not in the biological sense, but in their dynamism, their responsiveness, their capacity for transformation. And as September turned to October, as 3I Atlas continued its approach toward the sun, the green glow only intensified. The comet grew brighter, more active, releasing ever larger amounts of gas and dust. Observers noted the development of a faint tail, barely visible, stretching away from the nucleus in the direction opposite the sun as expected. But there were also hints of something unusual, something that would become more apparent in the weeks ahead. The beginnings of an anti-tail, a stream of material pointing not away from the sun, but toward it, a reversal of the expected pattern, a clue that 3I Atlas was not done surprising us. The transformation from red to green was more than just a visual change. It was a threshold crossed, a signal that the comet had entered a new phase of its journey. The dormant visitor had awakened. And as it hurtled deeper into the solar system, closer to the source of light and heat that was revealing its secrets, it would continue to change, to glow, to tell its story in wavelengths and molecules, in colors written across the void. The green was just the beginning. The brightest, most active phase of 3I Atlas still lay ahead, waiting at the point where it would come closest to the sun, where the heat would be strongest, the chemistry most intense, and the mysteries most profound. There's a moment in every comet's journey when it comes closest to the fire, when the distance shrinks, the heat rises, and everything hidden begins to surface. For 3I Atlas, that moment arrived in late October 2025, perihelion, the point of no return, the closest it would ever come to our sun before leaving forever. At that distance, roughly 120 million kilometers, the same orbital space where Venus circles endlessly, the temperature climbs. The ice responds, and the comet, glowing green, begins to do something unexpected, something that shouldn't happen. Its tail points the wrong way. By mid-October, observatories worldwide had been tracking 3I Atlas for over 3 months. The comet had brightened considerably since its green transformation in September. Its coma had expanded now, stretching over 100,000 kilometers across larger than Jupiter, though far more diffuse. Through telescopes, it appeared as a soft, glowing cloud with a bright point at the center, the nucleus barely visible beneath the haze of gas and dust. And extending behind it, a faint tail, pale and wispy, stretched for millions of kilometers, pushed outward by the solar wind and radiation pressure exactly as expected. But then, the Hubble Space Telescope took a closer look. On October 12th, as 3I Atlas reached approximately 1.5 AU from the Sun, Hubble's wide field, Camera 3 captured a series of high-resolution images in multiple wavelengths. The images were stunning. The green glow was clearly visible, concentrated around the nucleus. The tail extended properly, streaming away from the sun. But there was something else. Another structure. A faint extension of light pointing not away from the sun, but toward it. An anti-tail. A reversal of the expected geometry. Anti-tails are rare, but not unheard of. They were first observed in the 19th century and have puzzled astronomers ever since. The most famous example is Comet Rn-Roland in 1957, which developed a prominent spike pointing sunward, visible even to the naked eye. For weeks, observers debated what it was. Some thought it might be a jet of material being ejected toward the sun, defying physics. Others proposed it was an optical illusion, a perspective effect. The truth eventually determined was more subtle. An anti-tail isn't actually a tail at all. It's not material moving toward the sun. It's a sheet of dust particles lying in the comet's orbital plane, and when Earth passes through or near that plane, we see the sheet edge on, creating the illusion of a spike pointing sunward. But 3I Atlas wasn't quite following that script. The anti-tail observed by Hubble was real, a genuine structure, but its cause remained uncertain. Some scientists suggested it could be dust particles, ejected from the nucleus, with enough force to briefly move sunward before being swept back by radiation pressure. This can happen if gas jets on the sunward side of the nucleus release material with sufficient velocity. Imagine a geyser on Earth shooting water upward against gravity. For a moment, the water rises, fighting the downward pull before falling back. Similarly, dust particles could be ejected sunward, traveling a short distance before the relentless push of sunlight halted them and turned them back. Another possibility involved the nucleus's rotation. If 3I Atlas was spinning, and if active regions on its surface were positioned just right, they could jet material at angles that created complex structures. Comet 103P Hartley 2, visited by NASA's Deep Impact spacecraft, exhibited similar behavior. As it rotated, jets from different parts of the nucleus fired at different times, creating arcs and fans of material that didn't follow simple patterns. The spacecraft captured images showing carbon dioxide jets erupting from the ends of the elongated nucleus, spraying ice particles in all directions, some forward, some backward, creating a chaotic but beautiful display. For 3I Atlas, the rotation period was estimated at roughly 15 hours based on brightness variations. If we imagine the nucleus as an irregular potato-shaped object, perhaps 2 to 3 kilometers across, rotating slowly with active patches on its surface, releasing gas as they face the sun, we can picture how complex the resulting structures might be. Gas and dust wouldn't stream uniformly. they'd pulse jet spiral, creating patterns that shifted over hours and days. And if one of those jets happened to point nearly toward the sun, it could create the appearance of an anti-tail, at least temporarily. As 3I Atlas approached perihelion, the activity intensified. By October 20th, just days before the closest approach, the comet was releasing an estimated 200 kilograms of gas per second. That might not sound like much, but over hours and days it adds up. In a single day, the comet was losing nearly 17 metric tons of material vaporized ice and dust blown into space. And this rate was accelerating. Each day as the sun's heat grew stronger, more ice sublimated, more gas escaped, more pressure built beneath the surface. Temperature plays a critical role in this process. At Earth's distance from the sun, solar radiation delivers about 1,361 watts per square meter, enough to warm the surface to comfortable temperatures during the day. But at 1.5 AU, the intensity drops to about 600 watts per square meter, less than half. At 1.0 AU Venus's distance, it rises to roughly 2,600 watts per square meter, and closer still at 8 AU, which 3I Atlas would reach at perihelion, the intensity climbs to over 2,100 watts per square meter. For a comet, this difference is profound. The warmth penetrates deeper, more layers sublimate. Molecules that were stable farther out begin to break apart. Water ice, the primary component of most comets, sublimates at temperatures around -70 degrees Celsius in the vacuum of space. Carbon dioxide ice requires even less, sublimating at -78 degrees Celsius at standard pressure. But in vacuum, it can sublimate at much lower temperatures, as cold as -125 degrees Celsius. Carbon monoxide is even more volatile, sublimating below -200 degrees Celsius. So as a comet warms, these ices sublimate in sequence. First carbon monoxide, then carbon dioxide, then water. And with each transition, the chemistry of the coma changes. For 3I Atlas spectroscopic data showed that the gas cloud was dominated by carbon dioxide, with traces of carbon monoxide and only modest amounts of water vapor. This composition is unusual. Most comets are water-rich, often 80% or more water ice by mass, but 3I Atlas seemed to be carbon-rich with water as a secondary component. This suggested it formed in a colder environment farther from its parent star, where carbon-based ices could freeze solid, or perhaps it formed in a system with a different elemental abundance richer in carbon relative to oxygen. On October 28, 2025, 3I Atlas reached perihelion. At precisely 1423 UTC, it passed 0.8004 astronomical units from the Sun, about 120 million kilometers closer than Earth, but farther than Venus. At that moment, the Sun's gravity pulled hardest on the comet, accelerating it to its maximum speed, relative to the Sun over 240,000 kilometers per hour. The heat was at its peak. The surface temperature of the nucleus exposed to direct sunlight likely exceeded 200 degrees Celsius, hot enough to vaporize water ice rapidly. But deeper inside, insulated by layers of dust and ice, the temperature remained far colder, perhaps still below freezing. This temperature gradient creates stress. The outer layers expand as they heat, while the inner layers remain solid. Cracks form, fissures open. Gas trapped beneath the surface finds pathways to escape, sometimes violently. In some comets, this leads to outbursts, sudden releases of gas and dust that temporarily brighten the comet by factors of 10 or more. Comet 17Pu Holmes in October 2007 experienced an outburst so dramatic that it brightened nearly 1,000,000-fold within 24 hours, becoming briefly visible to the naked eye as a fuzzy yellow star. The cause remains debated, but one theory is that a large pocket of volatile gas trapped beneath a thick crust suddenly broke through, explosively decompressing and carrying vast amounts of dust into space. Astronomers watching 3I Atlas at perihelion were alert for similar behavior. Instruments monitored the brightness continuously, looking for sudden changes. But the comet remained relatively stable. It brightened, yes, but smoothly, consistently following the expected pattern as it approached the sun. No dramatic outburst, no fragmentation. The nucleus appeared to be holding together, at least for now. This was encouraging because many comets don't survive perihelion, especially first-time visitors. The sun's heat and tidal forces can tear a fragile nucleus apart, turning a solid comet into a cloud of debris. Comet Shoemaker-Levy 9 is perhaps the most famous example of tidal disruption, though in that case, the culprit was Jupiter, not the Sun. In 1992, the comet passed too close to Jupiter within the planet's Roche. Limit the distance at which tidal forces exceed the comet's internal strength. The nucleus broke into more than 20 fragments, which continued to orbit Jupiter until July 1994. When they collided with the planet one by one, creating spectacular fireballs visible from Earth. Each impact released energy equivalent to millions of nuclear bombs, leaving dark scars in Jupiter's atmosphere that persisted for months. For 3I Atlas, the sun's tidal forces at perihelion were weak, far too weak to disrupt the nucleus. But the heat was another matter. If the nucleus was loosely bound, a so-called rubble pile, held together more by ice than by structural strength, the rapid sublimation of that ice could weaken the bonds, allowing pieces to separate. This is thought to have happened to Comet Ison in 2013, as it approached perihelion, passing within 2 million kilometers of the sun's surface, far closer than 3I Atlas. The heat was so intense that the nucleus essentially evaporated, disintegrating into a diffuse cloud of dust that faded within days. But 3I Atlas survived. After perihelion, as it began to recede from the sun, it remained intact, still glowing, still releasing gas. Observations showed no signs of fragmentation. No sudden changes in brightness that would indicate a loss of structural integrity. The nucleus, whatever its internal composition, was strong enough to withstand the sun's embrace. And that survival meant there would be more to learn, more observations to gather as the comet continued its journey outward. One of the intriguing aspects of perihelion is what happens afterward. For many comets, the peak activity doesn't occur exactly at perihelion, but weeks or even months later. This delay, called the thermal lag, happens because heat takes time to conduct through the comet's material. Imagine heating a large block of ice. The surface warms quickly, but the interior remains cold, insulated by the layers above. Only gradually does the heat penetrate deeper, melting ice far below the surface. Similarly, in a comet, the warmth absorbed at perihelion continues to diffuse inward for weeks afterward, activating deeper layers even as the comet moves away from the sun. Scientists tracking 3I Atlas were curious whether it would exhibit this behavior. Would it continue to brighten after perihelion? Would new chemicals appear as deeper ice is sublimated? Or would it simply fade, cooling as it moved away, returning to dormancy? The answers would come only with patience, continued observation, and a bit of luck. Because shortly after perihelion, 3I Atlas disappeared from view, not because it had disintegrated, but because of geometry. From Earth's perspective, the comet passed behind the sun, entering the glare, becoming unobservable. For several weeks, it would be hidden, moving through that bright zone where the sun's light drowns out everything else. This conjunction, as it's called, is a common challenge in astronomy. Objects near the sun in the sky, whether planets, comets, or stars, become impossible to observe from Earth-based telescopes. Even space telescopes like Hubble and Webb have to avoid pointing too close to the sun to protect their sensitive instruments. So, for nearly a month from late October through mid-November, Atlas traveled in silence, unseen, changing in ways we could only imagine. Models predicted it would continue to outgas, continue to glow, possibly even brighten further due to thermal lag. But until it emerged on the other side, until it cleared the sun's glare, all we could do was wait. During that waiting period, scientists reviewed the data collected so far. They analyzed the spectra, the brightness curves, the images. They compared 3I Atlas to other comets looking for patterns, anomalies, anything unusual, and several things stood out. The carbon-rich composition, the exponential increase in cyanide production before perihelion, the nickel without iron, the anti-tail. Each observation deepened the mystery. This wasn't a typical comet, if such a thing even exists. It was an individual shaped by its own history, its own formation, environment, its own journey through the galaxy. Have you ever waited for something important knowing it's happening just out of sight? Knowing that when it reappears, it might be changed, transformed by experiences you couldn't witness. That's what the astronomical community felt in those weeks. Anticipation mixed with uncertainty. Would 3I Atlas emerge brighter or dimmer? Would it still glow green, or would new colors appear? Would it have fragmented, or would it still be whole? The questions hung in the air unanswered as the comet traced its invisible arc behind the sun. And there was another question, less scientific, but no less profound. What does it mean to watch something from another star system pass through ours? To witness an object that formed billions of years ago under a different sun in a different corner of the galaxy, now responding to our sun's warmth. In a way, perihelion was a meeting, a brief encounter between two stellar families. The chemistry of one star system, frozen in the ice of a comet, awakened by the light of another star. And in that awakening, we glimpsed something rare, a connection across the vast distances that separate stars, a reminder that despite those distances, the universe is connected, woven together by gravity and light, and the slow drift of matter through space. Perihelion passed. The moment of closest approach came and went, and somewhere on the far side of the sun, invisible to us, 3I Atlas continued its journey, glowing green, releasing its secrets, writing its story in molecules and light. Soon, it would reappear. Soon we would see what perihelion had done to it, how it had changed, what new mysteries it carried. And when it emerged, when telescopes finally locked onto it again, what they would find would confirm that this visitor from beyond was full of surprises, still glowing, still active, and perhaps even stranger than before. When something emerges from fire, it's never quite the same. The heat changes, it reveals what was hidden, strips away the surface to show what lies beneath. For weeks, 3I Atlas had been invisible, lost in the sun's glare, passing through its moment of greatest heat unseen. And when it finally reappeared, when telescopes found it again in late November, the question everyone wanted answered was simple: what had survived. On November 26, 2025, exactly 4 weeks after perihelion, the Gemini North Telescope in Hawaii captured the first clear post-perihelion images. And what they revealed was stunning. The comet hadn't faded. It hadn't dimmed or fragmented. If anything, it glowed brighter than before. And the green, that emerald hue that had first appeared in September, was now unmistakable, vivid, saturating the entire coma. The waiting had been difficult. When a comet disappears behind the sun, there's always uncertainty. Models can predict what should happen, but comets don't always follow predictions. They're too complex, too variable, too dependent on their internal structure and composition. Some comets brighten dramatically after perihelion. Others fade quickly, their volatile ices exhausted, their surfaces sealed by dust. And some simply disintegrate, unable to survive the sun's heat. Until you observe it directly, you can't know which path a comet will take. Gemini North's observation was part of a public outreach program called Shadow the Scientists, where students around the world could watch live as astronomers operated the telescope. On that November night, as the telescope's 8.1-meter mirror turned toward the coordinates where 3I Atlas should be, there was anticipation. The exposure began. Light from the comet photons that had traveled millions of kilometers struck the detector. Data accumulated. And when the image appeared on the screens, processed through 4 filters, blue, green, orange, and red, the comet was there. Whole, active, glowing green. The image showed the nucleus at the center, a bright point surrounded by a diffuse halo. The coma extended outward in a teardrop shape, asymmetric, brighter on one side than the other, suggesting active regions on the nucleus were jetting material, preferentially in certain directions. And there still present was the anti-tail, that faint spike pointing toward the sun, now even more prominent than in pre-perihelion images. The tail itself, the main dust tail stretched away from the sun, pale and wispy, millions of kilometers long, though faint and difficult to see against the background stars. What struck observers immediately was the intensity of the green. In the pre-perihelion images, the green had been present, but relatively subtle, mixed with other colors, dust scattering red and yellow light. But now, post-perihelion, the green dominated. It was as if the comet had fully committed to this color, embracing it, saturating itself with the molecules that produce that emerald glow. Spectroscopic analysis confirmed what the images suggested. Diatomic carbon C2 was being produced in enormous quantities, far more than before perihelion, and cyanide CN was also elevated, its emission lines bright and sharp in the spectra. This intensity suggested thermal lag was at work. The heat absorbed at perihelion when the comet was closest to the sun had continued to conduct inward-reaching layers that hadn't been warm enough to sublimate before. And those layers, it seemed, were exceptionally rich in carbon compounds. Perhaps they represented a distinct formation episode in the comet's history, a time when its parent star system was particularly carbon-rich. Or perhaps they were simply deeper, more pristine layers, less processed by radiation, preserving the original chemistry of the comet's birth. Scientists had seen thermal lag before in other comets. Comet Hale-Bopp, one of the brightest comets of the 20th century, visible even from light-polluted cities in 1997, exhibited strong thermal lag. Its peak brightness occurred several weeks after perihelion, as heat continued to work its way through the massive nucleus, estimated to be 60 kilometers across, far larger than most comets. Month after month, Hale-Bopp released gas and dust, maintaining its brilliant display for over 18 months, one of the longest-lasting cometary apparitions on record. Observers noted that the coma's color shifted over time, different molecules becoming prominent as different layers sublimated. For 3I Atlas, the post-perihelion observations revealed not just brightness, but complexity. The James Webb Space Telescope, with its infrared capabilities, observed the comet on December 3, 2025, looking for molecules that don't emit invisible light. Webb's spectrograph dissected the comet's light into thousands of wavelengths, revealing the chemical fingerprints of everything present in the coma. And the results were remarkable. Carbon dioxide CO2 dominated the spectrum, accounting for roughly 87% of the gas by mass. This was consistent with earlier observations, but now confirmed with unprecedented precision. Carbon monoxide CO made up about 9%, and water vapor H2O comprised most of the remaining 4%. This composition is extraordinary. In our solar system's comets, water is almost always the dominant volatile, typically 80% or more of the ice by mass. Carbon dioxide is present usually around 10 to 20%, and carbon monoxide is even less, often just a few percent. But 3I Atlas was inverted. Carbon dioxide was king. Water was the minority. This strongly suggested the comet formed in a very cold environment far from its parent star, where temperatures were low enough for CO2 to freeze solid in large quantities. In our solar system, that happens beyond about 5 AU from the Sun, the region where the giant planets orbit. But for CO2 to dominate so thoroughly, the formation region might have been even colder, perhaps 10 or 20 AU or farther. Alternatively, the parent star system might have had a different carbon-to-oxygen ratio than our Sun. Stars form from clouds of gas and dust, and the composition of those clouds varies depending on the history of the region. If the cloud that formed 3I Atlas's home system had been enriched in carbon from previous generations of stars, the resulting planets and comets would inherit that carbon-rich signature. It's a reminder that each star system is unique, shaped by its own history, its own sequence of stellar births and deaths. The water content low, as it was also revealed something interesting. Spectroscopes detected not just H2O, but also its breakdown products, hydroxyl OH and atomic oxygen O. When water molecules sublimate from a comet and are exposed to sunlight, ultraviolet photons break them apart through a process called photodissociation. The OH radical glows at specific wavelengths, creating emission lines that are easy to detect. By measuring the strength of these lines, scientists can estimate the rate at which water is being produced, even if they can't see the water molecules directly. For 3I Atlas, the OH emission was modest, consistent with the low water abundance. The comet was releasing only about 20 kilograms of water per second, compared to hundreds of kilograms per second for a typical comet at similar distance from the sun. But the carbon dioxide production was staggering. Estimates suggested the comet was releasing over 150 kilograms of CO2 per second in late November, and possibly more at perihelion. Over the course of a day, that's over 13,000 metric tons of carbon dioxide, enough to fill a small building. And this rate had been sustained for weeks, possibly months, meaning the nucleus must have contained a vast reservoir of frozen CO2 enough to supply this ongoing outgassing without depleting. One of the challenges in studying comet composition is distinguishing between what's actually in the ice and what's produced by chemical reactions in the coma. Not all molecules detected in the gas cloud around a comet were originally frozen in the nucleus. Some are created when larger molecules break apart under sunlight. For example, diatomic carbon C2 isn't present in the ice. It's produced when more complex hydrocarbons fragment. Similarly, cyanide radicals CN come from larger molecules like hydrogen cyanide HCN or more complex nitriles. So, when scientists report that a comet is rich in C2 or CN, what they really mean is that the comet is rich in the parent molecules that produce those fragments. In 3I Atlas, the parent molecules likely included a variety of carbon-bearing compounds. Long-chain hydrocarbons, organic molecules built from carbon and hydrogen, perhaps even more complex organics molecules incorporating nitrogen, oxygen, sulfur. When these sublimate and are hit by sunlight, they shatter, and the pieces C2, CN, CH, C3 glow in different colors, painting the coma with a spectrum of emissions. The green glow so prominent in the images was the cumulative result of millions of tons of these molecules breaking apart every day, each fragment fluorescing briefly before being destroyed in turn. X-ray observations added another layer to the story. The European Space Agency's XMM Newton Observatory, equipped with highly sensitive X-ray detectors, observed 3I Atlas on December 3rd for 20 hours continuously. X-rays from comets aren't emitted by the comet itself, but by the interaction between the solar wind and the comet's gas cloud. The solar wind, a stream of charged particles flowing from the sun at speeds of 400 to 800 kilometers per second, collides with neutral gas molecules in the coma. These collisions transfer energy-stripping electrons from the gas molecules and exciting them to high-energy states. When the ions relax, they emit X-rays primarily in the soft X-ray range wavelengths, between 0.1 and 2 nanometers. XMM Newton's data revealed a diffuse X-ray glow around 3I Atlas, confirming the presence of a substantial gas cloud interacting with the solar wind. The X-ray emission wasn't uniform. It was stronger on the side facing the sun, where the solar wind struck the coma head-on, and weaker on the trailing side, shielded by the comet's own gas. This asymmetry allowed scientists to map the structure of the gas cloud in 3 dimensions, revealing that it wasn't a simple sphere, but an elongated comet-shaped envelope compressed on the sunward side by the pressure of the solar wind. Japan's X-RISM satellite launched in 2023, and equipped with advanced X-ray spectrometers also observed 3I Atlas during this period. X-RISM's instruments could measure the exact energies of the X-ray photons, identifying which elements were emitting them. The data showed emission lines from oxygen, carbon, and nitrogen, all elements abundant in the molecules sublimating from the comet. By analyzing these lines, scientists could determine not just which elements were present, but their ionization states, how much energy the solar wind was transferring to the gas and how the interaction varied with distance from the nucleus. These observations painted a picture of a comet actively battling the solar wind. Gas streaming from the nucleus expanded outward, forming a protective bubble around the comet. The solar wind pressed against this bubble, compressing it, heating it, ionizing it, but unable to penetrate deeply. Inside the bubble, neutral gas continued to flow, molecules continued to fluoresce, and the green glow persisted. It was a dynamic equilibrium, constantly shifting, as the comet's outgassing rate varied with rotation, and as the solar wind's intensity fluctuated with solar activity. Throughout December, observations continued. Ground-based telescopes in both hemispheres tracked 3I Atlas nightly weather, permitting. Astrophotographers captured stunning images, some showing the green coma in exquisite detail, others revealing the subtle structure of the dust tail and antitail. Amateur astronomers with modest equipment could see the comet as a faint fuzzy patch, though the green color was challenging to perceive visually. Human eyes aren't very sensitive to faint green light, so most observers saw it as pale grayish green at best. But cameras with their ability to integrate light over long exposures revealed the true color vividly. On December 19th, the Reach Atlas made its closest approach to Earth, passing at a distance of roughly 280 million kilometers, about 1.9 AU. This was close enough for detailed observation, but far enough to pose no danger. At that distance, the comet appeared extremely faint to the naked eye, requiring binoculars or a telescope to see. But for instruments, it was an ideal target. The geometry was favorable, with the comet positioned away from the sun in Earth's sky, visible during evening hours for observers in the northern hemisphere. NASA's Europa Clipper spacecraft en route to Jupiter happened to be in a position to observe 3I Atlas from a different angle. Mission planners took advantage of this opportunity, commanding the spacecraft's cameras to capture images of the comet. Because Clipper was far from Earth, on a different trajectory, it saw 3I Atlas from a perspective unavailable to ground-based telescopes. The images revealed details of the comet's structure that were hidden from Earth's viewpoint, showing the three-dimensional nature of the gas cloud and how it responded to the solar wind. These multi-angle observations are rare and valuable. They allow scientists to construct a more complete picture of a comet's activity, seeing it not just as a flat projection, but as a fully three-dimensional object. In the case of 3I Atlas, the different perspectives confirmed that the nucleus was rotating, that the active regions were concentrated on one side, and that the antitail was indeed a real structure, not an optical illusion. As December progressed, the comet began to fade slowly but perceptibly. This was expected. It was now moving away from the sun beyond 1.2 AU by mid-December, and the decreasing solar heat meant less sublimation, less gas, less glow. But the fading was gentle, not abrupt. The thermal lag continued to sustain activity, heat stored in the interior, still driving sublimation, even as the surface cooled. Models suggested the comet might remain active for weeks or even months, more gradually dimming, as it traveled farther and farther from the sun. And yet, even as it faded, it remained green. That emerald hue, so unexpected at first, had become the comet's signature. Every image, every spectrum, every observation confirmed it. 3I Atlas was a green comet, glowing with the light of carbon, torn from ancient molecules, carrying with it the chemistry of another star, another world, another time. And in that glow, we saw not just beauty, but information. Data encoded in wavelengths, history written in atoms. A message from the galaxy delivered one photon at a time. But even with all these observations, all this data, mysteries remained. Questions that the green glow alone couldn't answer. Why was the composition so unusual? Why nickel but not iron? Why did the brightness follow such an extraordinary exponential pattern before perihelion? And perhaps most intriguingly, why did the comet's orbit align so closely with the plane of our solar system's planets? That alignment, with a probability of less than 1%, hinted at something deeper, something statistical models struggle to explain. And as we move forward, as we gather the remaining pieces of this puzzle, those anomalies will come into sharper focus, revealing just how strange, how exceptional this visitor truly is. Sometimes the universe leaves clues, small things easy to miss that don't quite fit, a number that's slightly off, a pattern that shouldn't exist, an alignment too perfect to be random. And when you notice these whispers, these quiet anomalies, they pull you deeper. They ask questions that have no easy answers. 3i Atlas carried several of these whispers, things that made scientists pause, recalculate, and wonder. Because this wasn't just a comet that glowed green, it was a comet that seemed to defy probability itself. The first whisper came from the comet's trajectory. When astronomers calculated the orbital path of 3i Atlas, tracing it backward and forward through space, they found something unexpected. The comet's orbit lay almost perfectly in the ecliptic plane, the flat disk where Earth and the other planets circle the Sun. This plane isn't arbitrary. It represents the original disk of gas and dust from which our solar system formed 4.6 billion years ago. Most objects born in our system, planets, asteroids, even many comets, stay close to this plane, their orbits tilted only slightly. But 3i Atlas wasn't born in our system. It came from interstellar space, from another star, arriving from a direction that had nothing to do with our solar system's orientation. And yet, when gravity from the Sun began to curve its path, it ended up traveling almost exactly along our ecliptic plane. The inclination, the tilt of its orbit relative to the ecliptic, was measured at less than 3 degrees. For an interstellar object, this is extraordinary. The probability of such an alignment purely by chance is roughly 1/5 of 1%, less than 0.2%. You could flip a coin and get heads 9 times in a row, more easily than you'd expect an interstellar visitor to arrive aligned with our planetary plane. Why does this matter? Because it suggests something beyond random chance. Perhaps the comet's trajectory was influenced by another object before it entered the solar system, bending its path just enough to align it. Perhaps it passed through the outer reaches of the Oort cloud, that distant shell of icy bodies surrounding the Sun, and gravitational interactions with those objects adjusted its course. Or perhaps, and this is where speculation edges toward the provocative, the alignment means something else entirely. Some scientists, notably Avi Loeb from Harvard, have suggested that such precise alignments could indicate artificial origins, objects designed or guided, rather than purely natural. Most astronomers disagree, arguing that, while improbable, the alignment is still possible through natural processes, especially if we don't yet understand all the factors that influence the comet's long journey through the galaxy. To put this in perspective, consider Oumuamua, the first interstellar visitor. Its orbit was tilted at roughly 122 degrees to the ecliptic, coming nearly perpendicular to the plane of the planets. That's what you'd expect from a random interstellar object arriving from an arbitrary direction, with no connection to our system structure. Comet 2I Borisov had an inclination of about 44 degrees, also far from the ecliptic, also consistent with a random arrival, but 3i Atlas less than 3 degrees, aligned, almost as if it knew where the planets were. Statistical anomalies like this are tricky. In astronomy, we observe billions of objects. With such large numbers, rare events become inevitable. If you flip a coin enough times, you'll eventually get 10 heads in a row. But that doesn't mean the coin is rigged. It just means you flipped it many times. However, we've only observed 3 confirmed interstellar objects. 3. With such a small sample size, finding one with a 0.2% probability alignment feels less like inevitability and more like a genuine oddity. It's a whisper, not a shout, but it's their persistent asking to be explained. The second anomaly involved the brightness curve. When scientists plotted how 3I Atlas's brightness changed over time as it approached the sun, they expected a smooth, predictable pattern. Comets typically brighten in proportion to their distance from the sun, raised to some power usually between 2 and 4. This reflects how sublimation rates increase with temperature. Double the solar heat, and you might triple or quadruple the gas production, which increases the brightness. It's a well-understood relationship modeled and confirmed in hundreds of comets, but 3I Atlas didn't follow that pattern. Its brightness increased far more steeply. Analysis of photometric data from July through October showed that the comet's luminosity grew proportional to distance raised to nearly the power of 10. Not 2, not 4, but 10. This means that for every step closer to the sun, the brightness increased by roughly a factor of 10. That's exponential explosive growth far beyond what sublimation alone should produce. And it wasn't just brightness. The production rates of cyanide and nickel followed similar curves, increasing by factors of 9 or 10 as the comet approached. Why would this happen? One possibility is a cascade effect, a runaway process where initial sublimation creates conditions that accelerate further sublimation. Imagine ice sublimating beneath a dusty crust. As gas escapes, it carries away dust-opening channels. More surface area is exposed. More ice sublimates, more channels open. The process feeds itself, growing exponentially until the available ice in that region is depleted or the structure collapses. This has been observed in some comets, though rarely to such an extreme degree. Another possibility involves the comet's internal structure. If 3I Atlas contained pockets of highly volatile ices, carbon monoxide, or perhaps even more exotic materials trapped beneath layers of less volatile ice, those pockets could remain sealed until the temperature rose enough to breach the barrier. Once opened, they would release their contents rapidly, creating a surge in brightness. If multiple such pockets existed, each at different depths, they could trigger sequentially, each contributing to the exponential growth. Or perhaps the explanation is simpler, and we're just not seeing the full picture. The data we have, while extensive, still represents only a fraction of the comet's activity. We observe primarily invisible light and certain infrared wavelengths, but other processes emitting at wavelengths we haven't measured could be contributing. Radio observations, millimeter wave spectroscopy, far infrared imaging, each reveals different aspects of a comet's chemistry. And 3I Atlas was observed intensely, but not in every possible wavelength at every moment. Gaps remain, and in those gaps, explanations might hide. The third anomaly is perhaps the most controversial. On the night 3I Atlas was first discovered, July 2nd, 2025, a gamma-ray burst was detected by the Fermi Gamma Ray Space Telescope. Gamma-ray bursts, or GRBs, are among the most energetic events in the universe, typically associated with the collapse of massive stars into black holes, or the merger of neutron stars. They release more energy in a few seconds than the sun will emit in its entire lifetime, and they're visible across billions of light years. This particular burst, cataloged as GRB 250702A, lasted approximately 7 hours, which is unusually long for a gamma-ray burst. Most last only seconds to minutes. The burst's direction in the sky was calculated, and it appeared to originate from a region close to where 3I Atlas was located, within about 17 degrees. Now 17 degrees is not a small angle, it's roughly the width of your fist held at arm's length, or about 34 times the diameter of the full moon. In astronomical terms, it's a fairly large uncertainty typical for gamma-ray detections, which don't have the same angular resolution as optical telescopes. But still, the coincidence caught attention. A gamma-ray burst detected on the same night an interstellar comet was discovered coming from roughly the same direction. Avi Loeb calculated the probability of such a coincidence. Given the number of gamma-ray bursts detected per year, and the typical angular uncertainty, the chance of a 7-hour burst coinciding within 17 degrees of any given object is roughly once per 670 years. Not impossible, but very rare. Rare enough to warrant further investigation. Was there a connection? Could the burst and the comet be related? Or was it simply a coincidence, a cosmic roll of the dice that happened to land on this particular night? Most astrophysicists favor the coincidence explanation. Gamma-ray bursts come from distant galaxies' events so far away that they occurred millions or billions of years ago. Their light stretched by the expansion of the universe arrives red-shifted, and we observe the afterglow fading over hours or days. There's no known mechanism by which an interstellar comet, a small icy body traveling through space, could produce a gamma-ray burst. The energies involved are incompatible. It's like comparing a candle to a supernova. But the timing remains curious, a whisper in the data, unexplained if not inexplicable. Some have speculated more creatively. If 3I Atlas were not entirely natural, if it contained some form of artificial component or propulsion, could that produce detectable gamma rays? In theory, certain advanced propulsion systems like antimatter engines or fusion drives might emit high-energy radiation. But this veers into the realm of speculation far beyond what current evidence supports. The consensus is that the burst and the comet are unrelated, two independent events that happen to occur on the same night in the same general direction purely by chance. Then there's the chemical anomaly of nickel without iron. We've touched on this before, but it bears deeper examination. Nickel and iron are cosmic twins. They form together in the cores of massive stars during the final stages of nuclear fusion. When those stars explode as supernova, nickel and iron are ejected into space in roughly fixed proportions, about 18 nickel atoms for every 100 iron atoms. This ratio is remarkably consistent across the universe, found in meteorites in Earth's core in the spectra of distant stars. It's a signature of stellar nucleosynthesis, the process by which elements are created. Yet, in 3I Atlas, spectroscopic observations showed strong nickel emission but weak to non-existent iron lines. This could mean the iron is present but not being vaporized, locked in larger grains, or bound in compounds that require higher temperatures to break apart. Nickel, being slightly more reactive chemically, might exist in forms that vaporize more easily. Or the ratio itself might be unusual, a genuine deviation from the cosmic norm, suggesting the comet formed from material processed in an atypical stellar environment. Perhaps a supernova with unusual composition, or a region enriched in nickel through some prior event we don't understand. There's also the possibility of observational bias. Nickel emits strongly at certain wavelengths that are easy to detect with ground-based spectroscopes. Iron emits at different wavelengths, some of which are absorbed by Earth's atmosphere or fall outside the range of common instruments. If most observations were conducted in wavelengths favorable to nickel detection, we might be seeing an apparent absence of iron that's actually just a detection limitation. This is a common challenge in astronomy. You can only measure what your instruments are sensitive to, and gaps in sensitivity create gaps in knowledge. Some scientists have compared 3I Atlas to a specific class of meteorites called enstatite chondrites. These meteorites, rare on Earth, formed in oxygen-poor environments and have unusual metal compositions. They contain more nickel relative to iron than typical meteorites, and they're rich in carbon compounds. If 3I Atlas formed in a similar environment, in a region of its parent star system where oxygen was scarce and carbon abundant, it might naturally exhibit these chemical quirks. It's a plausible explanation, though difficult to confirm without a sample. And that's the frustration with interstellar objects. We can observe them, measure their light, analyze their spectra, but we can't touch them. We can't bring them into a lab, break them apart, examine their minerals under a microscope. Every conclusion is indirect, inferred from photons that traveled millions of kilometers, carrying information encoded in wavelengths and intensities. It's detective work with incomplete evidence trying to reconstruct a story from scattered clues. Another intriguing detail involves the comet's cross-section, the amount of light it scatters. Data from the Atlas survey telescopes, which had been monitoring the comet since late March 2025 before it was recognized as interstellar, showed that the scattered light increased inversely with heliocentric distance to the power of 3.9. This is steeper than typical for comets, which usually follow an inverse square or inverse cube relationship. A steeper curve suggests the comet was activating more surface area as it approached, perhaps because heat was cracking the crust, exposing fresh ice, or because sublimation was creating a more extensive dust cloud. It's consistent with the exponential brightness increase, but adds another layer of complexity to the models. Have you ever looked at a cloud and seen a shape that seems almost intentional? A face, a dragon, a castle. Our brains are wired to find patterns even in randomness. It's called pareidolia, and it's why we see constellations and stars, canals on Mars, and faces and shadows. In science, we have to be careful not to let this tendency lead us astray, to avoid seeing design where there's only coincidence. But we also have to stay open to genuine anomalies, to patterns that genuinely don't fit, because sometimes those anomalies are the key to new understanding. 3I Atlas presented a collection of anomalies. Individually, each could be explained, dismissed, accounted for with existing physics and chemistry. The orbital alignment, rare but possible. The exponential brightness, unusual but not unprecedented. The gamma-ray burst, probably coincidence. Nickel without iron, observational bias, or a typical composition, but taken together all at once in a single object. The accumulation of low-probability events becomes itself a kind of anomaly, a meta-pattern that whispers something deeper. Perhaps that something is simply that the universe is diverse, that comets, especially those from other star systems, can be stranger than our models predict, that we've only observed 3 interstellar objects, a sample so small that we have no idea what's typical and what's outlier. Oumuamua taught us that interstellar visitors can be unlike anything in our solar system. Borisov taught us they can also be familiar. And now, 3I Atlas is teaching us that the range of possibilities is wider than we imagine, that chemistry and physics can combine in ways we haven't cataloged, and that every new visitor will challenge our assumptions. Or perhaps it means something else. Perhaps these anomalies are pointing toward a gap in our understanding a process or phenomenon we haven't discovered yet. Not aliens, not artificiality, but some aspect of natural astrophysics that we've overlooked because we've never had the right object to observe. Science advances through anomalies. When Uranus's orbit didn't match predictions, it led to the discovery of Neptune. When starlight bent around the sun more than expected, it confirmed general relativity. Anomalies are opportunities, invitations to look closer, think harder, imagine differently. As 3I Atlas continues its journey outward beyond Earth's orbit, beyond Mars, heading back into the cold from which it came, these anomalies remain. They're recorded in data, archived in papers, waiting for future scientists to revisit with new instruments, new theories, new perspectives. Perhaps one day when we have observed 10 interstellar comets or 100, we'll look back at 3I Atlas and realize it wasn't anomalous at all, just the first example of a type we hadn't encountered yet. Or Perhaps it will remain an outlier, a single strange visitor whose secrets we never fully unravel. Either way, the whispers persist. They remind us that the universe is not yet fully known, that despite centuries of observation and discovery, mysteries remain hiding in the spaces between data points, waiting for the right question, the right moment, the right instrument to bring them into the light. And as we gather what 3i Atlas has taught us, as we synthesize the observations and the anomalies into a coherent understanding, we realize that this comet's greatest gift might not be answers, but better questions. Every visitor from beyond carries a library, not written in words, but in atoms. In the ratios of elements, the structure of molecules, the way light bends through gas and dust. And when we learn to read that library even imperfectly, we glimpse something profound. Not just what the visitor is, but what it means. What it teaches us about the universe, about ourselves, about the fragility of knowledge. 3i Atlas came from another star system, glowed green as it passed through ores, and will soon vanish back into the dark. But the knowledge it leaves behind, the lessons written in its chemistry and motion, will remain long after the comet itself is gone. And those lessons change how we see everything. The first lesson is about diversity. For centuries, we studied comets from our own solar system, cataloging their compositions, measuring their orbits, watching them brighten and fade. And from those observations, we built models. We developed theories about how comets form what they're made of, how they behave. Those theories worked beautifully for objects born around our sun, but they assumed a kind of universality, an expectation that comets everywhere would follow similar patterns. Water, ice dominant. Rocky dust mixed in. Carbon compounds present but not overwhelming. This seemed reasonable. The laws of physics are the same everywhere. Chemistry doesn't change. So, why would comets? But 3i Atlas showed us the flaw in that assumption. It arrived carbon-rich, water-poor, with ratios inverted from what we expected. It wasn't wrong, it wasn't broken, it was just different. Formed in a different environment under a different star, where the balance of elements and the temperature gradients produced a different outcome. And this realization ripples outward. If comets can vary so dramatically, what about planets? What about atmospheres, oceans, the chemistry that leads to life? We've only studied one star system intimately our own. Every assumption we make about how planets form, what conditions are necessary for habitability, is based on a sample size of one, until now. Interstellar visitors like 3i Atlas expand that sample. They're messengers from other systems carrying direct physical evidence of conditions we can't observe any other way. The nearest star, Proxima Centauri, is over 4 light-years away. Even traveling at the speed of light, it would take 4 years to reach it, and we can't travel anywhere near that fast. Our fastest spacecraft, Voyager 1, launched in 1977, has traveled only about 0.002 light-years in nearly 50 years. At that rate, reaching Proxima Centauri would take over 70,000 years. We're not visiting other star systems anytime soon, but if objects from those systems visit us, we can study them here now with instruments we already have. This makes every interstellar object precious. Oumuamua passed through before we fully realized what it was, and by the time we wanted more data, it was already too faint too far. We'll never get another chance to observe it. Borisov gave us more time, and we used it well, but it came and went, and now it's gone forever. 3i Atlas is the third, and there will be more, but we don't know when. Models suggest several interstellar objects pass through the inner solar system every year, but most are too small or too faint to detect. We only see the larger ones, the ones that brighten enough to stand out. So, each confirmed visitor is a rare gift, an opportunity we can't afford to waste. The second lesson is about humility. Science operates on confidence intervals, probabilities, likelihoods. We measure something, calculate the uncertainty, and say, we're 95% confident the true value lies within a certain range. This works well most of the time. But occasionally something comes along that falls outside every confidence interval, that defies every prediction. And we're reminded that our models are approximations, not truth. 3i Atlas did this repeatedly. The orbital alignment, the exponential brightness increase, the chemistry that shouldn't be possible. Each time scientists had to revisit assumptions, recalibrate models, admit that something unexpected was happening. This is healthy. Science advances through failure as much as success. When a prediction fails, when an observation contradicts expectations, it means we've learned something new. The danger comes when we refuse to admit failure, when we cling to old models, even when data suggests they're incomplete. History is full of examples. For centuries, astronomers believed Earth was the center of the universe because the models worked well enough, and questioning them seemed unnecessary. It took careful observation of planetary motions data that didn't fit to force a shift. Similarly, the idea that continents don't move seemed obvious. They're solid rock. How could they drift? But geological evidence accumulated anomalies that couldn't be explained until the theory of plate tectonics emerged, transforming our understanding of Earth. 3i Atlas doesn't overturn any major theories, but it pushes boundaries. It shows that comet composition can vary more than we thought. It suggests that interstellar space might process materials in ways we haven't fully modeled. And it reminds us that 3 data points, 3 interstellar objects, are not enough to define a category. We need more, many more. And until we have them, we should hold our conclusions lightly open to revision. The third lesson is about the chemistry of planet formation. When stars form, they're surrounded by disks of gas and dust, the leftover material from the collapsing cloud that made the star. Over millions of years, particles in that disk collide, stick together, and grow. Dust becomes pebbles. Pebbles become boulders. Boulders become planetesimals and eventually planets. But not all the material becomes planets. Some remains as asteroids' rocky leftovers in the inner disk. Some remains as comets' icy leftovers in the outer disk. And some gets ejected, flung out by gravitational interactions, with planets becoming interstellar wanderers. The composition of these objects tells us about the disk they formed in. If a comet is water-rich, it formed in a region cold enough for water to freeze, but warm enough that carbon dioxide and carbon monoxide remained gaseous and escaped. That happens at specific distances from the star, depending on the star's brightness. If a comet is carbon-rich, it formed farther out where even carbon-based molecules froze. By studying 3i Atlas with its unusual carbon dominance, scientists can infer that it formed in a particularly cold region of its parent system, possibly beyond 10 or 20 astronomical units from the star. That's equivalent to beyond Saturn or Uranus in our system. But there's another possibility. The parent star itself might have been different. Stars vary in composition. Our sun is what's called a population-wide star, relatively young, by cosmic standards formed from gas enriched in heavy elements by previous generations of stars. But older stars, population 2 stars, formed from more primitive gas, lacking many heavy elements. And different stellar environments produce different balances of carbon and oxygen. If 3i Atlas formed around a carbon-rich star, where carbon was more abundant than oxygen, the chemistry of the entire disk would shift. Carbon dioxide and carbon monoxide would dominate. Water would be scarce, and any comets formed in that disk would carry that carbon-rich signature. This has implications for planetary systems around carbon-rich stars. If planets formed there, they might have atmospheres dominated by carbon compounds. Methane, carbon dioxide, perhaps even more exotic molecules. Their surfaces might be coated in carbon-based minerals, graphite, or even diamond rather than the silicates we see on Earth. And if life arose on such planets, it would have to adapt to a chemistry very different from our own. Life on Earth is carbon-based, but it relies on water as a solvent oxygen for metabolism. Life in a carbon-rich system might use different solvents, different metabolic pathways. It's speculative, but 3i Atlas opens the door to these questions, forcing us to think beyond the familiar. The fourth lesson is about detection and planetary defense. Interstellar objects move fast, and they come from directions we're not always watching. 3i Atlas was first detected by the Atlas Survey, a network of telescopes designed to find near-Earth asteroids that could pose a collision risk. But it wasn't recognized as interstellar immediately. Early observations showed an unusual orbit, but confirming it required follow-up calculations, verification. By the time we knew what it was, it had been in the inner solar system for weeks. If it had been on a collision course with Earth, we would have had very little warning, far less than the years or decades we'd need to mount a deflection mission. This highlights a gap in our preparedness. We're getting better at detecting objects within our solar system, especially those on orbits that bring them close to Earth. NASA's Near-Earth Object Program catalogs thousands of asteroids tracking their paths, predicting close approaches decades in advance. But interstellar objects are different. They don't follow the usual patterns. They come from outside, moving faster on hyperbolic trajectories we can't predict until they're already here. And if one were large enough and on a collision course, we might not have time to respond. The good news is that collisions with interstellar objects are extraordinarily unlikely. Space is vast and Earth is small. The probability of an interstellar object hitting us is far lower than the probability of a solar system asteroid doing so, and even that's quite low. But it's not zero, and as we improve our detection capabilities as we build more powerful telescopes and survey systems, we'll likely discover more interstellar visitors. Some will be small, like Oumuamua. Some will be larger, like 3i Atlas. And someday, perhaps, we'll detect one early enough to plan a mission to send a spacecraft to intercept it to study it up close, rather than from millions of kilometers away. That's the dream. Imagine a probe rendezvousing with an interstellar comet, matching its velocity, deploying instruments to measure its surface, its composition, its structure. We could answer questions that spectroscopy alone can't address. Is the nucleus solid or porous? What's the temperature gradient inside? Are there layers? And if so, how many? We could even collect samples scooping up dust and gas, analyzing them with onboard labs. Or if the mission were ambitious enough, returning them to Earth. Such a mission would be technically challenging, requiring propulsion systems that don't yet exist, and years of flight time. But it's not science fiction, it's engineering. And as technology advances, it becomes increasingly feasible. The fifth lesson is about time and perspective. 3i Atlas traveled through interstellar space for millions of years, possibly tens of millions. During that time, the galaxy rotated. Stars were born and died. The sun completed dozens of orbits around the galactic center, and the comet drifted silently, frozen unchanged, carrying with it the chemistry of its birth. Then, in the span of a few months, it passed through our solar system, warmed, glowed green, and departed. From the comet's perspective, if it had one, this was a brief encounter, a momentary disruption in an otherwise endless journey. But from our perspective, it was monumental. We detected it, observed it, learned from it. Telescopes around the world tracked it. Papers were written, discoveries were made. For humanity, 3i Atlas was a significant event, a milestone in our exploration of the cosmos. Yet for the comet, we were just another star briefly brightening its frozen surface before fading back into memory. This asymmetry is humbling. It reminds us that the universe doesn't center on us, that our importance is local, temporary, a flash in the vastness of time and space. But it also reminds us of something beautiful. Despite our smallness, despite the brief flicker of our existence we noticed. We looked up, saw a faint green glow, and asked why. We pointed our instruments skyward, gathered photons that traveled millions of kilometers, and decoded their message. We transformed light into knowledge, curiosity into understanding. And in doing so, we connected with something ancient, something from another world, another time. That connection, fragile and fleeting as it is, matters. It's what makes us human. The desire to know, to understand, to reach beyond ourselves toward the mysteries that surround us. The final lesson is about what we don't know. For all the data we collected, all the spectra and images and measurements, vast gaps remain. We don't know where 3I Atlas came from, which star, which system. We can trace its trajectory backward, but after a few million years, the uncertainties grow too large. The galaxy's gravity, the pull of passing stars, the slow drift of stellar orbits, all these factors blur the trail. We might never identify its home. Similarly, we don't know if it will encounter another star system in the future, or if it will drift through the void, forever gradually cooling until even the faint heat of distant starlight can't warm it, and it becomes a dark, silent relic, invisible and forgotten. We don't know if there are more objects like it, carbon-rich comets from other systems, or if it's unique. We don't know why it aligns so closely with our ecliptic plane, or whether that alignment means anything beyond statistical chance. We don't fully understand the exponential brightness increase, the nickel without iron chemistry, the gamma-ray coincidence. Each mystery invites speculation, but speculation isn't knowledge. It's a placeholder, a reminder that answers will require more data, better instruments, more interstellar visitors to study. And that's okay. Science isn't about knowing everything. It's about knowing what we don't know, asking better questions, and accepting that some answers will take time, maybe decades, maybe centuries. 3I Atlas has given us a gift not of complete understanding, but of deeper mystery. It's shown us that the universe is stranger, more diverse, more wonderful than we imagined. And it's invited us to keep looking, keep questioning, keep reaching toward the unknown, because every answer we find opens a dozen new questions. And in those questions, in that endless curiosity, lies the true beauty of science. As the comet continues outward fading from our telescopes, cooling as the sun's warmth dissipates, it carries those lessons with it. Encoded in its ice, in its trajectory, in the molecules it released during its brief encounter with our light. And we carry them too in our data, our papers, our memories. The green glow that appeared one September night transformed through October and now slowly dims as 3I Atlas journeys back into the dark. But even as it fades, even as the green gives way to silence, the knowledge remains. And from that knowledge, new understanding will grow, branching outward like the arms of a spiral galaxy, reaching toward futures we can barely imagine, toward discoveries waiting in the spaces between stars. There's a moment just before sleep when thoughts begin to drift. The boundaries soften. The day's sharp edges blur into something gentler, something vast. And in that space between waking and dreaming, the universe feels closer. Not as something distant and cold, but as something intimate, something we're part of. Tonight we've followed a visitor from another star. We've watched it arrive, transform, glow green, and prepare to leave. We've traced its chemistry, its mysteries, its whispers. And now, as it fades back into the dark from which it came, we're left with something more than facts. We're left with wonder. 3I Atlas will continue its journey. Right now, as you listen to these words, it's moving outward beyond Mars, approaching the asteroid belt, traveling at over 200,000 kilometers per hour. The sun's light still reaches it, but weakly. And the warmth that triggered its green transformation is fading. The sublimation slows. The gas cloud thins. The glow dims. In a few months, it will be too faint for most telescopes to track. In a year, it will pass beyond Jupiter's orbit, entering the realm of the outer planets, where sunlight is just a bright star in the sky. And in a few years, it will cross beyond Neptune, beyond the Kuiper Belt, back into the vast emptiness between stars. But it won't be the same comet that arrived. It's lighter now, having lost thousands of tons of ice and dust to the sun's heat. Its surface is altered, new craters and valleys carved by escaping gas, fresh ice exposed where old crust was blown away. The green molecules, diatomic carbon, and cyanide radicals have long since been destroyed or dispersed, their brief fluorescence extinguished. What remains is a darker, quieter version of itself, a traveler marked by its passage through our light. And in some way, we're marked too. Every person who pointed a telescope at 3I Atlas, every scientist who analyzed its spectra, every student who watched the live observations, every person listening. Now, we've all been touched by this encounter. We've glimpsed something from beyond our world, connected with it across the void, and learned from it. That connection matters. It reminds us that we're not isolated, that Earth isn't separate from the cosmos, but woven into it, part of a larger story, written in gravity and light. Think about the journey this comet has taken. Billions of years ago, in a star system we'll probably never identify it, formed from a disk of gas and dust, accreting grain by grain, molecule by molecule. Perhaps there were planets in that system, orbiting close to their star, while the comet formed farther out in the cold. Perhaps those planets still exist, hosting oceans, atmospheres, maybe even life. Or perhaps the system is long gone, the star, having exhausted its fuel, expanded into a red giant and collapsed into a white dwarf, or exploded as a supernova. We don't know. The comet carries no signatures of recent events, only the chemistry of its birth. At some point, something disrupted the comet's orbit. Perhaps a close encounter with a giant planet, a gravitational slingshot that accelerated it beyond the star's escape velocity. Or perhaps the slow cumulative tug of passing stars, gradually altering its path over millions of years until it broke free. Once ejected, it began a journey through interstellar space, through the galaxy, encountering nothing. No air, no warmth, no light strong enough to melt its surface. Just the faint glow of distant stars and the cold radiation of the cosmic microwave background. The afterglow of the Big Bang still permeating space at a temperature of 2.7 Kelvin, just above absolute zero. For millions of years, perhaps tens of millions, 3I Atlas drifted. The galaxy rotated around it. Stars moved. Clouds of gas and dust collapsed to form new stars, some of which lived and died in the time it took the comet to cross the space between suns. And then, by chance, or perhaps inevitability, its path intersected with another star system, ours. Gravity from the sun bent its trajectory, pulling it inward, and for a few brief months, it experienced warmth again. It sublimated, it glowed, it was observed, measured, wondered at, and now it's leaving, returning to the cold, carrying with it the faint memory of our sun's light. Will it encounter another star? Statistically, probably not. The distances between stars are so vast that even traveling at 200,000 kilometers per hour, it would take tens of thousands of years to reach the nearest one. And space is mostly empty. The probability of passing close enough to another star to feel its warmth is extraordinarily low. More likely, 3I Atlas will drift through the galaxy indefinitely, a solitary traveler frozen in dark until the universe itself changes in ways we can barely imagine. But here's the beautiful part. For a moment, we saw it. We noticed a faint green glow and asked why. We built telescopes, designed instruments, coordinated observations across continents, and decoded the light into knowledge. We learned about carbon chemistry, about thermal lag, about the diversity of comets, and the strangeness of interstellar visitors. We asked questions that have no easy answers, and in doing so, we honored the comet's journey. We gave it meaning, at least from our perspective. Does the comet care? Of course not. It has no awareness, no consciousness. It's a lump of ice and rock governed by physics indifferent to observation. But we care. And that's what makes us different. We're matter that has become aware of itself, atoms arranged in such a way that they can contemplate other atoms' light, that has learned to wonder about light. In the vastness of the universe, that's rare. Perhaps not unique, we don't know yet, but rare enough to be precious. Science is often described as a quest for truth, a search for objective reality. And it is that. But it's also something more. It's a form of connection. When we observe a distant comet measure its light, calculate its composition, we're reaching across the void, touching something we can never physically hold. We're participating in the universe's unfolding story, adding our small chapter to the immense narrative that began 13.8 billion years ago and continues now in this moment as you breathe and listen and wonder. 3i Atlas has taught us that the universe is larger and stranger than we imagined, that our models are incomplete, that every answer raises new questions. And that's not a failure, that's the point. If we ever reach a moment where all questions are answered, where nothing remains to discover, something essential will be lost. The universe is not a puzzle to be solved, but a mystery to be lived with, explored endlessly, approached with humility and awe. And so, the comet fades. Slowly, gently, the green glow dims until it's indistinguishable from the background stars, and then even those become too faint and it vanishes from our instrument, slipping back into invisibility. But the data remains. The images, the spectra, the measurements, they're archived, accessible to future scientists who will study them with tools and theories we haven't yet developed. Perhaps they'll find patterns we missed, connections we didn't see. Perhaps they'll answer the questions we couldn't. Or perhaps they'll simply marvel as we do at the strangeness and beauty of a green comet from beyond. Before we part, there's one more thought to carry into the quiet. When you look up at the night sky, you're not seeing the present. You're seeing the past. Light takes time to travel. The nearest star's light is over 4 years old by the time it reaches your eyes. Distant galaxies appear as they were millions or billions of years ago. And the comet we've been discussing when we observed it. We were seeing light that left its surface minutes ago. Photons carrying information about a moment already gone. In a sense, astronomy is history. We're studying the past, preserved in light, trying to reconstruct what happened, what might have been. But here's the wonder. That same light that carries the past also connects us to it. When you see a star, you're touching ancient light that traveled across unimaginable distances to meet your eye. You're part of its journey, the final destination, the place where the photon's story ends. And in that ending, something new begins. Knowledge, understanding, a sense of connection to the cosmos that transcends time and space. 3i Atlas glowed green for us. Not for itself, but for anyone who looked, anyone who noticed, anyone who cared. And we looked, we noticed, we cared. And in doing so, we transformed a lump of ice into a story, a chemical reaction into beauty, a visitor into a teacher. That transformation is what makes science not just an intellectual pursuit, but a deeply human one. It's how we make meaning from the chaos, how we find connection in the void, how we turn the cold mathematics of the universe into something warm, something personal, something that matters. There will be more visitors, more interstellar objects drifting through our solar system, arriving from stars we can't see, carrying chemistry we haven't cataloged. Some will be small and dim, passing unnoticed. Others will be bright, spectacular, impossible to ignore. And each one will teach us something, will challenge our assumptions, will deepen our understanding. The universe is generous that way. It keeps sending messengers, keeps offering lessons, keeps inviting us to look, to wonder, to learn. Thank you for drifting with me through this quiet journey, for following a green comet from arrival to departure, from mystery to deeper mystery, for staying curious, staying open, staying willing to sit with questions that have no immediate answers. That patience, that willingness to not know is a kind of wisdom. It's what allows discovery to happen, what makes space for the unexpected, what keeps the sense of wonder alive. Sleep well, friend. Let your mind drift where it will. Perhaps toward distant stars, perhaps toward green glows in the dark, perhaps toward nothing at all. Rest in the knowledge that the universe is vast and strange and beautiful, and that somewhere in that vastness, a comet from another star is traveling through the cold, carrying with it the faint memory of our light. And maybe, just maybe, that's enough. Dream gently. And when you wake, the stars will still be there, waiting silent, full of stories we've yet to hear. Good night.